Okay. So to recap what we have been discussing, first we discussed about the RCNN, right? So how can we first perform the regions proposal, and then we pass that each regions into a convolutional neural network. So which means that the COFNet has been looking at the different sections of image many times, right? So then there's another version called fast RCNN. So instead of just perform the region proposal first and then pass it into the neural networks. So instead we pass the whole network, pass the whole image first, and then we perform the region proposal later, right? So in order to classify where is the objects and then what is the object in that particular location, right? So that's the fast RCNN. So from previous class, as I mentioned, that even though fast RCNN has been very much improved in terms of performance in test time, however, there's a time that we have spent a lot of time in terms of test time. That is, if we include a region proposal, right? If we include a region proposal, we can see that the test time it takes 2.3 seconds to run. But if we take that out, if we take the region proposal approach out from the modules, so as you can see that there it is like much faster, 10 times faster. So the question is, can we do better? Like, can we remove this region proposal out of these modules, right? Even though fast RCNN, we still have to perform that. So the answer is yes, we can remove the region proposal out from the network. All right. So the thing that we can do is that instead of just manually perform the region proposal, so what we can do is that we can make a region proposal to be learnable region proposal. So which means that the modules will learn how to perform a region proposal, how to extract the regions from a feature map, so that we can extract an area from the feature map, so that we can classify where and what is the objects within the image. All right. So as you can see here, and instead of just manually performing region proposal, right? So we have another network that is learning how to extract the regions proposal from the feature maps. All right. So how does the region proposal network works? Right. So what we have to do is that first we just pass in the input image, right? Pass in into the CNN network as usual. So then what we're gonna get some sort of what we call the image features or the feature maps, right? So a result of a convolution we call feature maps or image features, right? So for example, here we pass in the color image, which is 3 by 640 and 480, right? And then we pass that in, we perform convolutions. So we probably end up with 512 times 5 times 6. So that is the dimensions of the image features, right? So and then for each features correspond to a point in the input. So we just have a set of some grid, right, mapping onto the input image, and then we take that the point in the input image. So we also map it into the image features as well, right? So that's what we did. So for example, imagine that we have the anchor box here, which is the blue block here, of a fixed size, right? For example, we have the anchor box over here of a fixed size at each point. So which means that these points also have to correspond to the point in the input image, in the image features as well. Right. So if you move the ankle, so the point in image features also move together. All right. So then what we have to do is that we want to classify each anchor as positive. That means there's an object inside that, or negative, which means there's no objects, right? For example, here we have a red rectangle, and with the anchor red over there, so which means the models classify these rectangles or anchor box as no objects or negative. All right, so we keep repeating doing this one. So we keep repeating that, and then we just pass this. All right, for example, we have this anchor box, and then we just take that part, pass it into a convolutional neural network, another convolutional neural network. So what we get here, we get the another anchor out. All right, 5 by 6, and then 2 over here. It just means that whether it has objects or not. All right. So yeah, that's why 2 are there. All right. So we keep doing this for many angle that we have. All right. And so we keep repeating doing this one. So the model is going to learn how to capture the angle, or how to capture regions. So how to divide it, the image features into different regions. So yeah, that's how the region proposal networks work, right? So yeah, maybe I just skip this one. So it basically it is nothing but so when the models predict whether any angles or any regions that is positive or negative, we have to compare with the ground truth, right? So if the predicted angle have the IOU greater than 0.7 with the ground truth box, any ground truth inside the image. So which means that we are going to classify that as a positive angle, which means that there's an object inside that region. All right. And also if it is less than 0.3, so which means that so there's no objects inside that region. So we keep doing this for each and every anchor point over here. So what we can do then, we can jointly training for losses, right? So for losses consists of classification losses and bounding box regressions losses. So bounding box regression means that we want to know the locations of the top or left and the width and the height of each region. So we want the model to predict that one. So which means that we have to measure the predictions between the ground truth and the predicted bounding box. So and these problems we call regressions because, for example, the models could predict, for example, at pixel 3 and pixel 4, something like that. So which means this is the regression problems. So it needs to predict a continuous value, right? And also for each and every regions that we got from region proposal networks, so we're gonna pass these regions to another neural network so that it can give us another classifications whether these regions that is being extracted by using RPN network, it is really contain an object, right? So that's basically what is faster RCNN, right? So if we compare the performance between RCNN, fast RCNN, and faster RCNN, as you can see, from fast RCNN to faster RCNN, it improved like 10x like speed in terms of test time speed. So which means that it improved very much in terms of inference time, right? So that's the fast RCNN. So if you look at this models, right? If you look at these models, we can see that it consists of two-stage object detection, right? So the first stage would be it will run once, right? It will run once per image. I think it just maybe probably this is this should be switching between this one and this one, right? So this is the first stage, and this is the second stage. All right, so the first stage here is that we have a backbone networks, right? We have a backbone networks that's run on the image once, right? And then after that, we're gonna get a image features. So then we're gonna pass these image features to the second stage. So then in image, using image features with regions proposal networks. So what we get out is we get a cropped features, right? We get a cropped features, and then we pass this each individual regions into another models, right? So then it will perform predictions. As you can see here, this is what we call the two-stage object detectors, all right? So the question is, do we really need the second stage, right? So the question is, do we really need the second stage? So the answer is no. We can perform this using single-stage object detection. Right? We can do that by using just one stage. Right? So if we look at this single stage, we can just pass it into a networks, and then after this one, after you get a region proposal, you don't need to pass that cropped regions into another networks because we already have this, right? So at this point, we already have that the models have a classification score and already predict a bounding box, right? We don't need to crop the regions again and then pass it into the models again. So we just remove the second stage and then left out with a single stage over here. All right.
So do we really need the second stage?
No, we don't need the second stage. So as you can see from here, so we can pass it into the network. So then we're gonna get image features, right? And then you just use this another networks to just predict for each individual's angle. So previously, what we are doing here, so what we are doing here is that we are using this network, right? We are using this network to predict a bounding box, to predict a regions of interest. And then we crop that region, pass it into the second network, which is what we call the ROI pooling over here. This is another network. So in which these models, we don't need it, right? We don't need another network here. We just cut it off here. All right, so that's what we call a single stage object detection. All right, so we just make this network to predict both classifications and also the bounding box locations. Okay. Right. So that's bring us to another example of models. One of the most popular object detection model, that is YOLO. Right. So YOLO is stand for you only look once. Right. So what does it mean is that if we look back at these models, fast RCNN, faster RCNN, or RCNN, the models have to look at the image several times, at least 2 times, right? So the concept of YOLO is that it says that we only look at the image once, right? For detecting and predicting a bounding box. So let's see how it works, right? So the first step that we need to do in YOLO, for example, if you have some sort of images, right? So you are going to divide this image into the S by S grid. In this example is 3, right? And then after you divide after you divide the image into S by S grid, so what you're going to do next is that you divide the image. I think just make something wrong here. So what we are going to do is that we are going to set the number of bounding box, the second stage. We are going to set the number of bounding box that each cell, that each cell have to predict. All right. So in this example, we are saying that so each cell, we want each cell to responsible for detecting at most 2 bounding box, right? So this green dot, blue dot over here is the center of each bounding box. So the bounding box can have like many size, right? So which cells is going to responsible for any particular bounding box? We can determine that by the centers of each bounding box, right? For example, this cell is responsible for these 2 bounding box because the centers of these 2 bounding box fall under this cell, even though the size of the bounding box just gone out from the cell. But what we are looking at is the centers of that bounding box. All right. So we keep doing this for every cell. All right. And then finally for each bounding box, right? For each cell, not bounding box. For each cell, we are going to determine the bounding box that has a confidence greater than some threshold. So we can set some threshold, right? So if there is more than one, so we can suppress it.
Step 2 is same.
Then yeah, I just missed typing here. So it is another, let me see what it should be.
Bounding box. We turn the box if the confidence is more than.
So I just missed typing. So the second one would be each cell predict B bounding box. Okay. So is it here?
Return the bounding box if the confidence is.
Each cell predict B bounding box.
And return bounding confidence threshold.
Này tức là có
Nó
cái
lên
kích
vị
thước
trí.
bao nhiêu bóng nó tìm cái điểm
Right.
Nó lên vị trí.
So in this example, each cell predict 2 bounding box.
thôi, nhưng mà cái B bằng 2 kia thì là tức là
So,
tạo 2 bao nhiêu bóng. Ví dụ như là
Dựng rồi. Thầy đây bọn tao thì không dạy thì that y should be equal to 2 in the step 2. Yes.
in this one,
Yes.
so we can set any number.
Yes.
We can set any number. You can set B equal to 2, 4, 5. So in the original papers, it said B equal to, I think, let me see. B is equal to, in the original paper, B is equal to 2, and then S is equal to 7. So N is the number of classes of an object. So it depends on you whether how many bounding box you want the model to predict for each cell. So we can set this parameters. So the more numbers of bounding box for each cell to predict, so the more time it takes for the models to make a predictions. So basically we can set this is equal to 2. So which means that in each cell there might be the 2 bounding box, and then the bounding box would probably be different size. So we want the bounding box that enclose the objects, which means probably we want the bounding box that has the bigger size in some case, but some case we might probably need a bounding box that is smaller size. So we give it variations of the size of the bounding box for each. So you can increase it into 3 as well, no problem.
In here there are 2 bounding box, right? And the area bounding box with variant to find the center point.
the two bounding box. So for each bounding box, right? For each bounding box, we are going to determine the centers of each bounding box. Why do we need to determine the center of the bounding box? Because we want to know which cell is going to responsible for detecting this. All right, so because the next step, we are going to make it into just a single bounding box left in each cell, right? So for example, here, if you look at the car over here, there are two bounding box, right? The car over here. So there are two bounding box, smaller one and the bigger one. So both are contain the objects, but the bigger one is the one that has the entire objects within it, right? But the smaller one is just partially of that. So if we compare the bounding box, the bigger one and the smaller one, if you compare with the ground truth, and then you're gonna get the bigger one that has the IOU greater than some threshold, which means that it gives you a better predictions when compared to the ground. All right. So the first thing we need to do in YOLO, we need to label the image. Right, we need to label the image. Right. So what do I mean by labels? So if you have this image, at the very first thing you need to do is that they use human to draw this bounding box. All right. So in this image we have one object. So when the model predict, we have to compare these predictions to this ground truth, and then we have to compare this prediction to this ground truth. All right, so what we're gonna get, this one is higher IOU, the bigger one, higher IOU. The small one here, we have a smaller IOU. All right, so then what we have to do is that we have to suppress the one that has smaller IOU. Right. Right, so let's take this as an example, okay? So let's take the most simple case, all right? So let's say that we are going to divide the image into 3 by 3, right? Let's take this very simple as an example, so that the more complex case just follow the same the same approach. Okay, for example, here. We are going to divide the image into a 3 by 3 cell, 3 by 3 grid cells. And then for each grid cell, we are telling the model that you can predict only one bounding box for each grid cell, right? So in this case, we are taking the most simple case first. So which means that just one bounding box per one grid, right? So and then for each bounding box, so let's say that in our data set, we want to detect either a dog or a human. All right, so just 2 objects first. So when we pass this image into the neural network CNN, the models is going to predict a vector Y. So the vector Y consists of P, which is a probability of the bounding box containing an object. Okay, and then Bx and By, which is the coordinates of the centers of each bounding box. Right, and then we have width and height of the bounding box, and also we have another parameters, that is the probability the cell is going to contain the object belong to a dog or a human. So this is what the models is going to predict, right? For example, if the models give you 1 and some value of Bx, By, and Bh, Bws. So 1, this indicate that the bounding box contain an object, right? If the model give you this, but if the model give you 0, which means that this bounding box does not contain an object. And also it needs to give you the coordinates of the centers of each bounding box, so that we can determine which cell is responsible for this bounding box. Okay, and then another two would be, it would tell us that if the bounding box contains an object, what kind of object it is containing in that bounding box. So in this one, it is telling us that it's contain human, because we have either a dog or a human, right? So what if we increase the number of bounding box that the model can predict per grid cell, right? For example, here we say that the models can predict up to 2 bounding box, all right? Only 2 bounding box per grid cell, all right? So the blue one and the red one here. So the output from the models is going to be these many vectors, right? This vectors consists of 10, how many? 10, 12 elements, all right? So the first 5 will be the bounding box informations and the probability whether the bounding box contains objects or not. And then another 5, the second 5 elements, it is going to describe the second bounding box. And then the last 2 elements would be telling us whether this bounding box containing which objects, right? So if you look at this one, this grid cell, the green grid cell over here, it has 2 bounding box that fall under that grid cell. Okay, so what we are going to get here, so since the blue bounding box, it has a human inside this object, inside this bounding box, right? So what we're going to get is that we're going to get this element is equal to 1, and then we're going to get xy of this bounding box coordinate, that is this dot over here, and then the size of the bounding box. All right, for the red bounding box over here, it is going to get 0 because it doesn't contain any objects inside it. And then it's going to give us also x, y, h, and w of this bounding box. And then the model is going to predict whether out of these 2 bounding box, which objects it's contained. So it's either humans or a dog. For example, in this case, we're going to get 0 and 1. So that is telling us that this bounding box belong to this grid cell containing human, right? So if you look at the size of the output, if you look at the size of the output from the models, from the CNN models, we're gonna get that it will have a total of S by S times the number of 5. So 5 is this, 5 come from this number. 5 come from this number of elements. So that's 5, okay? And B is the number of bounding box per grid cell. B is the number of bounding box per grid cell. In this case, B is equal to 2. All right, and C is the number of objects that we want the models to predict. For example, in YOLO version 1, it is capable of predicting 20 different classes of an object. All right, so C will be 20 in this case. And then in the original papers, they use this equal to 2. So, and then this one is equal to 7, right? I'm not sure, yeah, 7. So this is the size of the output from the models, okay? So any questions? Any questions? So I hope this is clear. This concept is clear. So how YOLO is trained, how it is trained, right? So so we know that each grid cells can produce multiple predicted boxes, so at least 2 boxes, right? From the original papers. So the question is, which one should we use as a final predicted bounding box? All right. So during training, right, during trainings, we are going to choose the one with the highest IOU. So from this example, the blue bounding box is the ground truth. The green one is the predicted bounding box with respect to this grid cell. Okay, with respect to this grid cell. So during trainings, the big green bounding box, that's what we're going to choose because it has the highest IOU when comparing to the other one with the ground truth. Okay. So during inference mean when we use it, when we test it, right? During inference, we are going to use a non-maximum suppressions. The non-maximum suppressions, I hope you remember this from previous class. So if the IOU of P1 and P2 greater than some threshold, we are going to select the one that has the highest predictions classification score. Okay, so in this case, we are going to choose the P1, right? Because P1 has a highest IOU. All right, so any question from this overview of this, how you get from divided image into a grid bounding box and then the confidence score. So any questions from online? All right, so that's how it is being trained. So another elements whenever we train the models, first we have to have a models, we have to have a data set, right? We have a data set, and we have to pre-process the data set. And then another important element in each and every or almost machine learning models have to do is a loss function. You have to come up with a loss functions. So the loss function is going to tell you whether the models perform good or bad, right? So if we look at the YOLO loss function, it consists of two parts, right? So it consists of loss of locations and the loss plus the loss of classifications, because in object detections, what we have to do is that first we have to find what is in the image, right? What is in the image? And then the second thing that we need to answer is where is the object within the image? So that's why we have allocations and classifications, right? So let's first look at the classification, right? So the classification is simple, right? So we just need to determine whether that bounding box contains objects or not. All right, that's simple as that. All right, if the bounding box should contain an object, it should predict as 1. Otherwise, it will be 0. All right, so we can just use a mean square errors for the probability of that, and then sum it all over within each image. Right, so that's a classification score. And for the locations, right? For the location, we have the confidence score. So if you remember when we do this predictions, right? It has a classifications. So PC here is the classification score, whether any particular bounding box contain an object or not. But if we are talking about what kind of objects it's contained in that bounding box, we have to look at this C1 and C2 over here. All right. So that's why we are going to use that to compute the locations. Okay, to compute the locations loss. So the location loss is telling us whether the locations or the bounding box coordinates that is predicted by the models, how much it is deviate from the ground truth, right? So that's why we have xi minus x cap I. So this is ground truth, right? So xi is the ground truth. Xi is the ground truth, and then this is the predicted value. So this is the centers of each bounding box, right? S and Y. And this one is just the size of the bounding box. All right, it's just the size of the bounding box. So we just compute this, how much this deviate from the ground truth, and then how much this size of the bounding box deviate from the ground truth. So the lambda here is just used to regularize the whether you want to give the weight to which part of the loss functions, more or less. So you can choose this value. Okay. And another part would be the C, right? CI. So whether the objects, what class of object that is being detected in that particular bounding box. So it's just a matter of that. So yeah. So that's the location loss. Right. So we just find the mean square errors of that of each of these elements. All right, which means that most of the loss function that is being used in YOLO is mean square errors. All right, it just comes down to the regression problems. So we just measure the mean square errors from the ground truth. Right. So what is the limitations of each grid cells? So each grid cell can contain only one classes. So I have to note that here, the limitations of YOLO version 1. Okay, so this is the limitations of YOLO version 1. So from YOLO version 2 onwards, so each grid cell can contain multiple objects in it. So they have addressed this limitation, but for the YOLO V1, so each grid cell can contain only one class. All right, and then each grid cell can contain only finite number of bounding box. So that is, we set the bounding box to 1, 2, 3, either one of that one. Okay. So the bounding box prediction start with the unusual aspect ratio. So if the image just straight in or straight out, because when we divide the image into S by S grid, even though the same image, if we have stretched the image into a different aspect ratio, so the objects from one, for example, if we have, let me draw this one. So let's say that we have the image at this aspect ratio, right? And then we have the objects over here. We have the objects over here. And then we divide this into this grid, right? And then if we stretch the image, so this only the cell that contain the objects. But if we stretch the image into a different aspect ratio, probably we stretch it out in the horizontal. So probably the object would be somewhere around here, right? And then if we divide it into a 3-part, into a S by S grid, so instead of from this grid cell, it moved to this grid cell. All right, so that's another limitations of this YOLO. All right, so it's just the same errors in the small box is worse than the larger box. All right, so if you have a larger bounding box, the errors in the small bounding box, it is going to be worse than the errors in the larger box, because if you look at these equations, right, because it takes a square of that one. If the small bounding box, when we take a square of that, we would get a very high errors, because we are taking a square of that, right? So the errors in the small box will be worse than the large box. All right, so mini grid cell do not contain an image. I mean, do not contain the objects, right? So we probably have mini grid cell that contain only the background, no object at all. So this would probably the training confidence score would probably be pushed to 0. So that's why they have this lambda to control whether which one you want to give a weight, to give a much higher weight from that. Okay. Right. So in summary, from the past two classes, we have talked about the object detections algorithms or models. We can split them into two categories, that is two-stage or proposal, right? So this consists of RCNN, fast RCNN, faster RCNN. So that's what we call two-stage. And the other one would be a stage-free proposal, all right? I mean, a single stage. So it consists of SSD, single stage detector, and the other one would be YOLO, right? So these are the two categories of object detection models that we have learned so far from the previous class and this class. Okay. Any questions? So I'm not going into vision transformer because there's a lot of math in there. So what I want to do is I want to walk you through the code. So I think I already have shared the code for today, right, in lab 9, I believe. Lab 8 or lab 9. Yeah, lab 9. So you can grab the code as well as the image. All right. So I have put some sample data over here. So we are using a Pascal. We are using this image. Let me see. So we are going to use this data set, Pascal Walk YOLO. So it's contain like some 16,000 images. That's too much, right? So we cannot run that much without GPU. So I'm to give you some sense of what we can do with YOLO. So I just take a sample, 100 samples from there, and then we are going to try to train that. Okay, so what the image looks like, the image going to look something like this. Train image. All right, so this is the image that we are going to use. So yeah, so one image probably have many objects, one probably have a single object, something like this. Okay, so these are the example of the image that we are going to run, right? So let's just so first you grab the code from here and also the data set, right? So let me wait for you to just setting this up. Just probably copy into your Google Drive. So you can grab it from lab 9. So in these folders, I have 4 another subfolders over here, which is for training and testing image. So we have testing 100 images, and then training 100, and then test for 10. So in this lab, we are not using the pre-trained models, right? So for the real application, you would better use a pre-trained model. Just grab some weight from there, and then fine-tune it instead of just training from scratch. right? So let me know when you're ready. And can you copy the data from the photo?
Yes.
Okay, okay. So for the YOLO architectures, it is nothing special. Okay, YOLO architecture is very simple. Okay, it's very simple. So, but what we have as a models here is that let's see. So if you look at the architectures of YOLOs, it is nothing but just a simple CNN models, right? It consists of how many ones? 1, 2, 3, 4, 5, 6, 7 layers, 7 CNN layers, right? And then one fully connected layers, and then the final output would be the size of 7 by 7, that is S by S, right? S by S grid, and then multiply with 30. So for each with cells, it has a 30 dimensions of that vectors. So the 30 dimensions come from 5 multiply B, that is 2, right? And then plus a number of class, that is 20. So we're going to have 10 plus 20, that is 30. So that's why the output at the end over here is 7 times 7 times 30, right? So 30 came from there, right? So the model is that the architecture is very simple, right? So let's just run this first import the torch. All right, so let me just connecting to that. All right, so so what we are going to do here, we just set the architecture configurations, right? Architecture configuration would be the size. The first element would be the size of the filters, right? The size of the filters. The second elements would be the numbers of filters, right? The number of filters, and then this one would be the stride, and then the third one would be, I think, what is it? The output. Okay. So it is 7 times 7. It is 7 times 7. Okay. So this is the channels, I believe. This is the channels. This is the numbers of this one. And then M is a max pooling layers, right? M is max pooling layers. So the max pooling is 2 by 2, and then stride 2. Okay. So in here, 7, the kernel size, 64 is a filter site, 2 stride, and then 3 is a padding. Okay, so we are keeping doing the same. Convolutional layers, max pooling, convolutional layer, max pooling, and then consists of another 4 convolutional layers followed by max pooling. All right, so we just keep doing that. It just matters of you can decide yourself how many layers you like. Right? It depends on the complexity of your data set. Okay, so this is the configurations of the architectures. Okay, just simply run that, and then here is how we define the CNN block, right? So the CNN block, we will just define the class of that one, right? So we can have in channels, out channels, right? So define the first layer, this layer CNN layer self COF, which is the 2D COF, right? In channel, out channels, and it had no bias, batch norm, right? Batch normalizations, and then the activation function would be ReLU. This is one single CNN layers. Okay, and then we are going to construct the architectures of YOLO version 1. Okay, so what it takes is that the architecture config, which is from here. So this is the architecture configurations from here. It takes in that, and then it takes in the in channels, that is the image of our image. And then we are going to define this create COF layers. All right, we are going to define this one. And then, so what does this do is that it is going to define this part of the models. Okay, this part of the models, this part. Okay, up to this part. So and this is one is the last layer, fully connected layer, that is this layer. Okay, so what we are going to do here, the create COF layer, the create COF layers. So we are just taking in these configurations, that is we divided here. So we define whether how many layers are there, and then what the configuration of these layers, what is the filter size, number of filters, paddings, stripes, something like that. So so we are just looping because what we are creating here is just a list, right? So we are looping into each of this. Okay. So so we are creating each COF layers, right? Because if you look at this one, we are going to create each COF layers over here. So that's why we are going to use this function to create that. Okay. So we are taking out the configurations from architecture list, and then we are setting, right? We are setting these parameters because we already defined the CNN blocks over here. We already defined the structures of CNN blocks. So for each layer, it consists of convolutional layers, batch norm, and then leak ReLU, that is activation function. So that's we define one layer. Okay, so this is one layers over here. It consists of convolutional layers, and then the batch norm, and then activation function. So that construct give us the one layers over there, right? So what we are doing here is just feed in the configuration that we are taking out from the list. Okay, so here we are checking whether if the thing that we are take out from the list is a tuple, so which is these are the tuple, right? This is a string, or this is a list. Okay, so if it is a tuple, so that is a convolutional layer. So that's why we are using this one. Okay, and if it is a string, that means it is max pooling layers. And if it is a list, which means that it consists of multiple convolutional layers in that part. Okay, so we just repeat that how many convolutional layers. So if you look at these parameters, if you look at this, so it has one Kopf layer over here, one max pooling layers over here. And then if you look at another one, this is one Kopf layers, and then this is one max pooling layers. But if you're looking at this one, this is a series of convolutional layer, right? So these are 1, 2, 3, 4. So that's 4 convolutional layer, and then followed by max pooling layers, right? So this is a list. This is a tuple. This is a string that we define. And also, if you look at another one of this one, it will be a list of that, and then followed by max pooling. So you keep doing the same. So that's why we have a list of convolutional layers in here. So that's why we have a list of this one. Okay, this is the list of that, and this is another list. All right. So we just keep it repeating that, and then we are using in the signature, which means that we just concatenate them together to construct the whole network. All right. So and then finally we create a fully connected layers. That is the layers at very end over here. This 4096 elements over here. All right, 4096 elements. And then we add some dropout. So what is the purpose of adding dropout? Any ideas? Why do we need to add dropout?
Regularization.
Yeah, right. So the adding dropout to add the regularizations. So what the dropout mean is that, let's say that you have 10 neurons, you have 10 neurons. And then if you're saying dropout equal to 0.5, which means that 50% of those neurons is going to be deactivated during the back propagations. Yeah. So when you perform a calculation, you just take them out, half of them out, yes. And then the rest will be used for calculation. So it will be shuffled around. It doesn't fix whether which neuron you are going to drop out. So it just randomly. So this help the models. This prevent the models from overfitting, right? If you are training the models and then your models seem to be overfitting, so you add dropout. So it will help, right? You add dropout as a regularization factors, or instead you add regularizations in the loss functions. So you can use that as well. And then finally we are having this prediction, which is equal to S times S, that is 7 times 7, and then times 30. All right, which is each cell, the predictions of each cells, how many boxes are there, right? So that's 30. That 30 come from that's 5 times B, that is 2. C is the numbers of classes, that is 20. All right, so that's how we define these architectures. All right, and then we just here is nothing but you just create an instance of that class. Okay. What happened? Oh, I didn't run this. Right. So this is how your model looks like. Okay, it consists of 27 CNN blocks, right? It consists of 27 CNN blocks over here. Right. So let's just let's just try to like pass in some random value over here, just a dummy to test our models, what it give out. Okay, so so we just doing like a batch of 2 images with this resolutions, just to test whether the model works. Okay, just randomly input any dummy images. So that's what you get out, because we are passing in 2 images, dummy images, and then this is the numbers of projected value that we get out. Okay. So so this is RGB, right? 3, and then 448 is the resolutions of the image, a dummy image. So here we are just connecting to the photos, because in these photos we have this .py dataset.py and the util.py. So if you go into this dataset.py, so we are let me download. So what we are doing here is that we are defining the dataset, right? We are defining the dataset. Where is the image photos, and then what is the number of grid, number of bounding box, and number of classes that we are going to use with our model, right? So it's predefined as 7, 2, and 20. Okay, and then here we are defining the functions to give us individual images. All right, you just get an items from a batch, from a stack of images. So that's what it does here. So it just go through the photos and then give you one image at a time. If you request a batch of 8, it will call this 8 times. So it will give you 8 images. Okay, and then if any transformations you want to perform with your models, I mean, you want to perform with the input image, you can do so here. So the transformations, for example, you can do data augmentation, like rotation, translation, give more brightness, give more, make it more darker, something like that. So to give variations to the data set, so you can do it here, right? And here we just convert this into a cell, right? So because we define S times S, C5 plus B, so that the number of grid, so this is the number of bounding box plus the number of classes, right? So for each box, we are going to define these 5 parameters, class labels, whether it consists any objects or not. X, Y is the centers of the bounding box, and width and height of the bounding box. All right, and then the class level you just convert it into integers. All right, so this one you just calculate the cell, whether which pixel belong to which grid cell. All right, because for example you have the image of 448 times 448, and then these many numbers you divide it into 7 by 7 grid. So you need to know which pixel belong to which grid, right? For example, if you have image of 748 times 748, if you divide it a grid into 7 by 7, what is the pixel number 100 is going to be in which cell? The pixel at location X is equal to 10, Y is equal to 20. Which cell this XY is in? So the question is, this is your image, right? This is your image. 48 pixel width, and then 48 pixel high. So we divided this into 7 grid cell. Right. So the question is, which of this cell, so this is S equal to 7, right? So if we have a pixel at X 10, Y 20, which of this grid cell is this bounding box going to fall into? Which of this? So this is going X, right? This is going X. This is going into Y. So what is the width of each grid? How many pixels each grid going to contain? So 740, 48 divided by 7. How many? 64. So this is going to be 64, right? So if X is 10 pixels, Y 20 pixels, so it will fall somewhere around here, right? So this pixel is going to fall under this first grid cell, right? So that yeah. So this is how we determined the bounding box with respect to, I mean, the centers of the bounding box with respect to the grid cell. All right. So that's how it's done. Okay. And in the utu.py, we're so here we're just use this to compute the IOU. Right, we just use this to compute the IOU, just give the box predictions, right? So for each box predictions, we're gonna get these 5 numbers. So this five number for each box in each grid cell. So for each grid cell, we're gonna have how many? 30 numbers, right? 30 numbers. So 20, which is the class numbers, and the numbers of the bot that is correspond to the bounding box will be 10 numbers, because we are saying that one grid cell can have maximum of 20, I mean, can have maximum of 2 bounding box. So that is the 10 value. All right. So this is gonna be 7 times 7 times 30. So this is bounding box, and also the label as well. So we are just using the predicted value to find the middle point. Okay, so this is just to calculate the middle point of, because it predict X and Y, right? And then this one just to find the corners of that. And then this is how you calculate the intersections over unions of the bounding box. And this is how you are going to do a non-maximum separations. And you look at you want to get the bounding box that has the highest IOU. So that's what you did, the non-maximum separations. Right. The rest is just how you calculate the average precisions. Okay. So we just load that in from there. And here we are defining the loss functions. Okay, the loss functions. Lambda 0.5 and then 5 from this value. That's it. Here, right? 5 and 0.5. And this one, it's just how you calculate the IOU and the highest IOU, and then calculate the box coordinates. right? You calculate the box coordinate, compare with between predictions and the ground truth. Okay, so you just take that. So basically what we are doing here is we just follow these equations. Okay, because we are doing we just follow these equations, right? It's just nothing but these equations. So what we are doing here. All right. And the object loss, the bounding box loss, coordinate loss, that is the coordinate loss, that is this one, that is coordinate loss. And then this one is confidence loss. And another one would be the classification loss. All right, so that's what we basically do here. All right. So let's just run there. So you guys have any questions? You follow? So any questions from on site? All right, so next we're just defining the hyperparameters, right? So the hyperparameters would be, for example, the learning rate, the batch size. So we can use like 16, 8, or 64 in the original papers. So this one, it depends on how much RAM you have, right? So it depends on your RAM of the GPU or the CPU. Yeah. So, and this one is the number of epoch that you want to run. So we probably make it down to like, let's say 500. But so the number of worker is just how many CPU you wanted to use. So this one you just ignore it for now, and then this just the image directory. Okay. So this one is nothing but just for the transformations functions, right? If you remember that in here, where? So we have the image transformations somewhere around here, I think. Where is it? Transformations. So here, yeah. So we have a transformations here in when we define the data set, right? So we have also need to define whether we want to make any transformations or not. Okay, so that's why we are adding these classes. So we're going to perform some transformation, that is resize the image, any image. So we are resizing to 448, and then we just convert that to tensors. So that's the only transformation that we are going to do. Okay. Yeah. And then this training function, it is nothing but you just pass in the train data loaders, the models, the optimizers, and the loss function. You pass that in, and then this one is your training loop. Okay, so for each batch of the data, you just push the data into the device. It's either CPU or GPU. Okay, and then pass it the input data into the models. The model give you the predictions. You use that predictions to calculate the loss value, compare the predicted value with the ground truth. All right, and then you just keep accumulating the loss value so that later we can compute the mean loss. And this one, the optimizer dot zero grad, which means that we want to make the gradient to zero first, and then we perform a back propagations, and then we just add the optimizer steps. Okay. So that's the only thing that we need to do in training loop. Right. So here's the main functions. Here's the main function. We define the instance of the models, right? So S7 B2 number of classes, put the models parameters to the device. And then this is our optimizer. We use a DAM optimizer. And then with this running rate, that is, I think 2E minus 5, that is 0.0005. Okay. And then with the weight decay. And this is our loss functions. So this one is nothing but if you have, for example, while you're training, you want to save the weight periodically. You want to save that at a checkpoint. For example, you train models for 1,000, and then at the epoch number 700, that's where your model get the highest accuracy. So you probably want to save that state of weight. So that's what we call checkpoint. So we probably can perform checkpoint every 100 epoch. So our models is going to save the weight every one epoch.
We zoom training.
Yeah. And then this one is we just define the data set, right? So specify the CSV, transform the input and the label. And this is the test data loaders. Test data set. So we have a data set, and then we need to feed the data set into the data loaders. So the data loader will take care of how we feed the models into, how we feed the data into the models. For example, the data loader will take care of shuffling the input data, or it will be perform something else. Okay, so it will, for example, at epoch 1, you feed in the first, at epoch 1, you feed in image 1 to 100. And then epoch 2, the data loader will first shuffle the image first, and then we give you another batch of the image, and then feed it into the models. Okay, so there are many parameters that you can play around with this one. And this is another one that is the test loaders. All right. And this one is just the training loops. So for each epoch, you just get the bounding box, finding the average positions, and then run the training loops. Okay, so the training loop. So this will be your batch, right? So number of batches in that one. So it loop to when it goes into these functions, it loop through number of batches, which means that all your data set will feed it into the models once in here, and then it start another epoch, come here, and then run this again to go to another epoch. Okay.
The mean average.
So if you don't want to do this function, you can copy everything here. You can copy everything here. You can copy, you can copy everything here and paste it here. So this one will make this one epoch. It will loop through this. So this is one batch. This is one epoch. Okay. But this way it much cleaner for each epoch. So you separate between the epoch and the batch. So how many batch in one epoch? This is how many epoch you want to train. Okay. So I think when you run this one, you're gonna run into some errors. Okay. So yeah. So can anyone solve this problem? Can anyone solve this problem?
Remote.
Change the runtime.
Yes. Runtime and change the runtime time
Right.
to using CUDA.
This one,
Yeah. Besides CPU, we change to default GPU.
CPU,
Yes.
okay. It works.
I don't know.
Kernel GPU. Runtime tab, it should be kernel
Python,
GPU.
Python 3, right? Yeah.
Sure, you sure?
Python 3 to the CPU.
Choose the CPU because CPU T4.
T4.
And if you
Hardware accelerator.
Okay,
Yes.
that's it.
And GPU.
That's it, right?
yes, correct.
Okay, okay. And can you guys run it?
We need to
May
run
not
from the
define
beginning.
look at all.
We need to run all from the beginning.
Okay. Let's see, it works.
Cái này một cái chuyện này chắc sẽ
Because this code is for because last year I taught this class in AIT, a master student. So in AIT we have a server that we have a GPU. So yeah,
vui quá.
so you guys doesn't have the access to the server, right?
You don't have.
And I'm buying the Google Colab Pro already. Pro Plus, $50.
50 or 20?
50.
Oh, that's expensive. Last,
Yeah, that's 1 month, then finish.
because last year I bought is $20. It's very, very slow. Is it running?
Yes, it runs.
Okay, okay. All right. It takes some time to calculate something. So you can see there, we have a GPU jumping up 8 gigabyte. I think there's some room for us to increase the batch size. So TP4, so I think we can make it up to, I'm not sure 32 is going to work. So yeah, as you can see here, the loss value is going down, right? So it is going down. The mean loss is keeping going down. So we have, how many we have? We have 100 images. We have 100 images for training. Okay. So what is missing from here? Anything missing from here? Anyone spot something that is missing from here?
What's wrong?
Yeah. So in this note,
What's missing?
yeah, in this notebook, there's some critical step is missing. Can anyone spot what is missing from this code? From the best practice that we have to do when we're training the models.
Validation. Cross validation.
Yeah. So you're right. So how do if I want to add validations, if I want to add validations, where and how should I do?
You're gonna put when you train loader in the data loader, you have to break into the cross validation at that steps when you fit and you set the validation cross validation at like 5 or 10. So maybe data loader you have to break that data into like 80-20 in that data loader train data loader. Break that one into 80-20 and cross validation for like 5 times, let's say. So maybe the fitting to the each iteration epoch is the step. That's what I think.
So what you're saying is that this is what we are training, right? This is where we are training the models, right? So the thing that we need to do when after training, we need to validate, right? Which means that the models gone through all the data in the data set first. That's the training, right? And then after that, we are going to validate it here, right? Validate. So which means that we need a validation functions over here. All right. So after validation functions, so in this validation functions, what you have to do is that you have to set the no grad, right? No grad, because during validation, you don't want the models to update the weight. All right, you need to set the models torch dot no grad, something like that. So to freeze the weight of the models, right? So this is one critical steps in here. And then after you perform validations, here is where you want to save a checkpoint. Okay, so that's why the AI is suggesting.
So,
Right? So,
a question.
Yeah.
The picture is more. If your data set is valid, the validation is not suitable here.
but we just
No,
we
we
just
still need to do.
we still need to do to see whether the model is overfitting or not. Yeah, questions.
Yeah, the point is I want to ask is, let's say that we have 100 pictures totally, let's say, and then we break only 80 image for training, 20 image for testing. We separate folders, and then we do the cross validation when let's say in 80 image we spread into 80 and 20 for each fold, which means that 60 for training and 16 for validation. So each for training, we do everything, back preparation, update grading, and then we validate on that 16 for, let's say, accuracy at a metric for each airports. And then we continue do that for each fold, for each airport, we do that one for each, and then for each airport. For each fold, we have, let's say, 100 airports, so we do that hundreds of times for one fold, and then 5 fold. Is it, a good approach as well?
So when you are talking about cross validations, right? So let's say that you have this 100 image.
Yes.
In your training, okay, in your training data set. Okay, so the cross validation is that, let's say that you want to perform five-fold, which means that you split this image into 20, 20, 20, 5 times, right?
Yes.
Okay, this 20, another 20. So for when you want to do cross validation, is that first you are training the models, with this 4.
Yeah.
And then validating with this one.
Yes.
Okay, that's one epoch. Okay, that's one epoch. And then the next epoch, you're using this 4 for training, and you are using this one for validations.
Yeah.
Okay, you keep repeating that in the cycle. So until you reach the maximum of epoch, you like to you like to train. So for each epoch, you have to look at the validation loss and the training loss to check
Yes.
whether the models is overfitting or not.
Yep.
Yeah.
Yes. Yeah, clear.
Mhm.
That's the approach still valid. Thank you.
Yeah. So here, after you are training and validate your models, you probably could, for example, give some criteria whether you want to save the models or not. You want to save a model's weight or not. For example, if let's say that if means average precisions greater than 0.8, let's say, you say that you want to save this only the case. This is only the case that you want to save the model parameters. Otherwise, you won't save it, right? There's no need for us to save the model's parameters if the models didn't perform well, right? So we can give these criteria whether how we want to save the models. All right. So after we save the models, and then next time we want to train the models with the new data, we can retrieve this checkpoint and then train from that point again. Right? Instead of just starting over again. So we are starting at the point that we already trained the models. So you can set this load model file. So the model file that you save, it will be in this format. All right, and then you just set this load model to true. And then before you're training, if load model is true, it means that it is going to retrieve the models parameters for the weight of the models from our previous checkpoint, so that we can continue training the models. All right. So this will help us in terms of, let's say that for now we have only like 10,000 images, and then in the futures we probably have more data, so we can just training from there, not starting over for the beginning.
Yes.
All right. Mhm. So yeah, I think the loss is going down, and the mean average precision is quite good because it's only 100 images. Of course, because this model's architectures is too big for this data set, so it seems to be overfitting, I would say, because here we didn't implement the validations. All right, so I think we have some time. So can you guys implement the validations and then we run it again? I'll stop training on my side. So can you implement this validation functions? So you can use this testing. You can use this test image as a validation. Okay. Can you implement the validations real quick? Use this data from the test image 10 as a validations image. All right, probably we can have like 15 minutes. You can implement this validation function.
A question.
Yep.
So in case that if we tie up, then the model is overfitting. Let's say that the accuracy like 90% and the validation is 80%, or yes, it's 10% gaps. And we keep continue training, but the gap is still there or even worse. but when you do the on the test sets, it's really the good performance. So what we're gonna do? Optimize reduce the overfeeding, or just just
Oh, so
performance really good already.
okay, right? So let's say that this is your loss function, right? So this is the loss value for training, let's say, and then this is the loss value for validations, and so here is still good, right? And then at some point the validation loss keep going like that.
Yep.
So here, this is what we call the model is diverge. All right, the model is diverging, not converging. So
Yep.
if it is converged, it has to go something like that. So the cost of models diverging, the cost of the model diverging, there are many costs, but what you can do from the training perspective, what we can do is that if you look at the gradients curve, for example, the gradient curve, something like that. So when it diverge, probably, so for example, if we have this gradient, right? And then we are stepping down somewhere around here, we are stepping down. The model diverge happen when we don't have a proper learning rate. Okay, when we don't have a proper learning rate. So probably when we get here, the model would jump out and then it would jumping around. It would jumping around like that. It didn't come down somewhere around here. So this is because the learning rate, right? Because when we are training the models, the thing that when we're stepping down the gradient curve slope, the amount that we're stepping down is corresponding to the size of the learning rate. Okay, so if your learning rate is too small, it will take a long time to converge. If your learning rate too big, it will overshoot, which means your model is diverging. But the thing that we saw that it just somehow it seemed to be converged, and then after that it diverged, which means that at this area, the learning rate that we are setting, it doesn't work. For example, if we fix the learning rate is equal to 2e minus 5, right? So all the step that we are taking here is 2e minus 5. So what we can do is that we can do one thing we can do adaptive learning rate, or we call learning rate decay, right? So learning rate decay means that as the epoch goes up, we can reduce the size, the value of the learning rate. So there are many algorithms that you can do. First, you can do a step like this. So for example, you say that after 50 epoch, divide the learning rate by 10. After 50 epoch, divided by 10 again. So this is what we call step. Or you can use some sort of, I think, exponential something. I don't remember the name. This is the exponential, or there's a function in PyTorch that you can do a learning rate decay as well.
Okay.
Yeah.
Understand.
So that's how we can address the divergence problems.
Clear. Thank you. But I need to do a lot of money to Google Colab to experiment.
Yeah. Right. So I'll give you like 10 more minutes to writing these functions. I don't have the solution. All right. So to be honest, I don't have the solution for this because I didn't write the validation function for this. So you can practice by doing validations.
I think first we have to split the train CSV.
No, you can use this one. So we already have defined this test loader, right? So for now, we can use a test loader as validation data set first instead of that. So what you have to implement is how do you use this data set as a validation? So you have to write another functions here, all right, to perform a validation. If anyone finish and then you wanna share, you're very welcome. Okay, finish. All right, so basically what you have to do is, first, you specify the path, right? You specify the path to the image dataset folders first, right? So that's what you have to do first. And then next, you have to write this validation function. It's pretty much the same, except that we don't have this step, okay, in validations, right? And then this is your validation function, okay? And then in the main loop here, you are changing these labels and image dimensions as well as this one, right? And then this is the test loader, so we don't have to do anything with it. So another thing that we have to do is first, right? We set the model to train mode, right? So this is what we call, this is how we set the model to training mode, model.train, all right? And then we pass these models to the train function. It start training, calculating back propagation, calculating the gradient. After finish one epoch, so we are setting the models to evaluation modes, right? So when you set the models to evaluation mode, it is going to disable the dropout. All right. So here we are using dropout during trainings. All right. So when we are setting the models to evaluation mode, it is going to suppress the dropout layer. So in validation or in testing, or in the inference time, we don't want to use the dropout. So that's why we are setting this so that the dropout doesn't take into account. And then we use these context managers to say that the models run under these context managers. We are not going to compute any gradients, or we are not going to do any back propagations. All right, so we just run this validation functions and calculate the test average precisions and the bounding box. All right, and then we just run that one. So just our memories. Yeah. So probably maybe I need to pay more, so we can get the GPU with more RAM. Yeah. So what you can try to do with this one is try to change the batch size. Okay, reduce the batch size probably to 4. I think 4 maybe enough. Yeah. So that's how you do the YOLO training. All right. Any questions? All right, so if no questions, I will turn this to the presentations. Okay. Yeah. Okay. So also don't forget to submit your presentations and any resources in Teal, because I saw that there are only 7 submitted documents in Teal. Okay. Okay, you can. Yes.
I sharing the screen now.
Okay.
For the mini project, I try to do to perform the panorama function at
Mhm.
the good space. This one and I add the panorama function in here
Okay.
and try to run the line. To keep the filter and so we see at the good base and add a panorama function.
Mhm.
Now I try to stick to panorama mode space and capture it image.
Okay.
Okay. Yeah. Not very well, but
Mhm.
try to turning this.
Okay.
Still keep the filter and it's at like this. Keep filter and geometry mode as the original could be.
Okay.
I try to do AI but it's not work.
Okay.
Yeah.
Okay. Which where did you get stuck with the AR?
The application has when it detects the cheat.
So it's trying to connect to your iPhone,
Yeah.
and you just
Yeah.
just keep running it. So then you keep disconnecting from the iPhone cameras. Or the other one, you can set the parameters of the video. So if you go to the parameters of the video, if you go to the code, you can set the parameters of the video, because if you're using Mac, it will first detect your iPhone
has
first.
a camera. Yeah.
Yeah, and
Yeah.
then you
This
can
one,
set,
right?
yeah, you can set that to one.
To one is switch to the camera of the iPhone.
No, so 0 is iPhone.
0 is iPhone. I think 0 is the camera of the Mac.
It depends.
Ah,
My Mac 0 is iPhone, and then one is the built-in webcam. Yeah.
okay. Let me check it again.
Mhm.
Let's see. I try to do many things, but finish the panorama functions.
Okay, so what about the other filters, something like that?
Yeah, làm rồi blur any and bright. Try to yeah, and gray
Mhm.
blur bright.
So that's the
Scroll.
track bar works.
Yeah.
Okay. right? Okay, okay. So for the AR, have you finished the calibration? Can you do the calibrations? Did you get stuck
Yeah.
with calibrations?
Okay, yeah.
Oh, okay. I'm not sure. So what, it didn't say anything.
It said that missing to require position movement,
Uh-huh,
frame height and frame width.
okay, okay. I see. All right, so there are two persons who haven't submit the presentation is you, right?
Yeah.
You Viet. And the other one, I'm not sure.
Sorry, how many?
Pham Quoc.
Hùng.
Oh, okay, okay. So, Hung, can you submit the presentations and other resources?
Not.
No,
This
no.
is still here. Yeah.
This one, right?
Yes, right.
Okay, okay.
Hùng ơi, thầy
You can speak, I think it's good. All right, so I think maybe this is it for this morning, and then the afternoon we are coming back for this class. So we are going to discuss about image segmentations in the afternoon. All right, any questions? Yeah, yeah.
The next one is the transformer.
No, we haven't discussed about segmentation. Yeah. So we are so next we are going to talk about the image segmentation. So I think we're not going to discuss about the vision transformer in this class. So today afternoon image segmentation, tomorrow generative models in the mornings, and then in the afternoon we will discuss about the 3D visions, 3D deep learning. Yeah, so we are going to wrap up the class for tomorrow with 3D visions.
Make some fish. They mean.
All right, so I will see you in the afternoon at 1.
Okay. I have to go and visit in China
Okay,
tomorrow. So
Okay.
I cannot sort in tomorrow. And in the final exam, I am still in China. So
okay, so you are going tomorrow, and then when are you coming back?
so in I'll be in China in 8 days. So
Mhm.
in the next Sunday, I have to enjoy the final exam.
Mhm.
So can I please carry another day of final exam?
Yes, so you're coming back on 20.
I come back on Tuesday,
22nd. Okay, so maybe probably how about 26?
Ngày 6 thì được không? Được.
Yeah, because we're
It's a work day. I
take the exam
bố trí
in the evening.
in the evening. So because we are actually want student to sit here, so then we can monitor the exam. So that's what we have been discussing. So students just sit in the room, so then I will come online and then like take you guys to the breakout rooms individually, so then I can record the monitors, the screen.
So if on the next Sunday in the final exam, can I take the exam online or
So you mean 20? This next Sunday, right?
the in the final exam day?
Yeah,
Can I
Uh,
join online from China?
so you can join live, but you have to have one camera pointing at you and then sharing the screen.
Yeah.
Okay, yeah, that's works.
mà nếu mà
So,
nó có một cái rủi ro ấy là nếu mà nó bị đứt mạng đứt nước là phải coi mà nhất là ở nước ngoài mạng nó không ngon đâu. Because I always tell him that the risk is network in China is not good, and when is during the final exam, if the network is disconnect.
Because I think if in China you have to use VPN,
Yes,
you have to
maybe.
use VPN.
But I'm not sure I will read this
Không vừa phải.
Yeah, when
Rồi,
it's the exam, you have to be free.
Còn đi ra ngoài ăn đi xong rồi bạn nói tiếp.
Like như thế nào?
Try lunch with us.
Yeah, sure. Where you guys going?
Of course, I cannot translate to Thai language. Do you know this one?
Tại quá. Tắt tiếng rồi.
Yeah.
Or yeah.
Không tắt được.
Yeah. Có nghe gì không?
Nghe anh mà rè quá đó, echo. Rồi đó.
Right. So let's get started. So in this afternoon, we are going to talk about image segmentations. All right. So we have already seen the object detections, right? So next, image segmentations. So in this class, we are going to learn both the classical image segmentation like k-means and mean shift. And then we are going to learn about the learning-based image segmentations. For example, those are semantic segmentations, instant segmentations, and panoptic segmentation. So these are one that we are going to learn. We are going to touch a little bit about each of these topics for today. All right. So if we look back to the computer vision task, all right, so we have seen classifications, we have seen object detections, and now we are going to discuss about semantic segmentations and instant segmentations. All right. So semantic segmentation is nothing but there's no object; it's just a pixel. We want to classify, to differentiate or to group a pixel only, right? So we don't want to know what is this pixel is, but we just want to know which one or which pixel that belong to the same objects, same surface, something like that. And for the instant segmentations, we are not only interested in what kind of pixel it is, but we are also interested in what are the objects that pixel belong to. All right, so that's instant segmentations. So before we dive into another algorithm about image segmentations, how we can do image segmentation. So let's first talk about what is image segmentation, right? So the very first image segmentation technique would be a binary segmentation. So binary segmentation is nothing but you just subtract the pixel value, right? So the pixel value would be either 0 or 1, right? So you have for example, here you have a grayscale image, and then you cut off, you set some threshold, you set some certain threshold. If any pixel that has a value greater than this threshold, you're going to keep it. Otherwise, you're going to remove it. All right. For example, this image of this coil. So if we set some threshold, so what we are going to end up is this image. So that's what we are going to end up with. So we set some certain threshold so that we can remove some of the pixel, right? So that's what we call a binary segmentations. So what about this one, right? So this coil is very simple, right? So you probably can find a very simple threshold. But what about this one? How can we segment the image into a very meaningful regions, right? For example, if you look at this group of people, right? So they're sitting next to each others. Some of them wear a hat, some of them have a long hair, some of them have a short hair, something like that. So how can we segment the image into some meaningful regions? How can we know how many people are there? Where's the bicycle? Where is the grasses? Where is the trees? Where is the buildings? Right? So how can we do that? All right. So If we look at how humans as a human, how we do a segmentation and grouping, right? So there's a theory called gastro psychology, all right? So if you look at this image, what do you see? What do you see in this image?
Black and white.
What do you see in this image?
You mean object?
Yeah, objects.
Water.
Hmm?
Spread it out.
What object do you see? Do you see a dog?
No.
You don't see a dog?
I guess.
Where
Okay.
is it?
How do you see it?
Dog.
So this is a dog.
No.
How do you see a dog?
Impossible.
So the thing that if you look at it real quick, right? So when you see a dog, you see the whole body of the dog first. All right. After that, you will recognize, oh, this is the dog as a whole. This is a dog as a whole. This is the head of the dog. This is the body of the dog. This is a leg of the dog. All right. So what gastro theory is about is that it is a theory is about that we as a human, we perceive a complex scene as a composed of many group of objects. So we see the whole object first, and then after that we can recognize the part of that object later. Right. So gastro means that just grouping, something like that. Okay. So that's how we as a human recognize or segments or grouping the objects within the image. So in Gestalt psychology, there's a certain numbers of principles that how can our human brain going to segment or group the object together. So the first principle would be a proximity principle. All right. If you look at these objects, and then if those objects are grouping together and then they are apart from each other, they are apart from other groups. So from one group, right? From one group in the top row, in the middle row, we're gonna recognize that we have three groups, right? For two objects in each group. And in the below the C here, so we're gonna see that as four groups, right? So that's what we call a proximity, which means the distance. The distance makes us as a human grouping different numbers of objects. All right. And another principle would be a similarity principle. So similarity in the sense that the shape of the objects, the color of the objects, or the orientations of the object. So these are another principle that when it is triggers our brain, so we are trying to, our brain is going to try to group the object that have the similarity together, right? For example, we have these objects with different colors, with different size, something like that. So yeah. And the third principle would be a common fit. What do I mean by common fit? Right? For let's say that we have these four objects, right? These four objects, and if these objects are moving in different directions, so our brain will try to group the object that are moving in the same direction as one group, right? So that's what we call common. And another principle would be common regions or connectivity, right? So if you look at this one, instead of just having the green objects, we have a red regions over here that encompass these two objects. So our brain is trying to group them together. And also, if we have a link or connections between the objects, our brain also trying to group them together as well. And another would be the continuity principle is that our brains also trying to group the object that has a curvatures. So if they are continuous, we are trying to group them together as one object. And the last one would be a symmetry principle, right? So if there are parallels or they have some sort of symmetrical features, so our brain also trying to group them as the same objects, same region, something like that. All right. So these are the principle that human brains are trying to segment or grouping objects within the image. And another problem with our brain, sometimes we got the illusory contours, right? For example, here, so actually there's no, if you look at the image on the top left corners, so actually there's no triangle, right? But our brains trick us to see the triangle within the image, right? Or the lower left over here, actually there is no circle, but by looking at this one, our brain trying to come up with a sphere. All right, so that's what we call the illusions. And also segmentation is very subjective. Okay, it's very subjective. So what do I mean by subjective? So if I assign each and every one of you to do a segmentations of the same image, you would probably end up with different segmented regions, right? For example, in this example, we have user 1, user 2, and user 3. So they were asked to perform a segmentations. So as you can see, each one of them, they have draw a different region. They have draw different segment, even though they are given the same image, right? So that's why the segmentation is kind of subjective. It's very, very subjective. Okay. So the segmentations are kind of intuitive for us as a humans, but it is very hard to translate this intuition to the algorithm. All right. So the strategy that we can use to tackle this problem would be there are two parts. So the first would be top-down segmentations. So we want to find some sort of algorithm that classify whether the pixel belong to the same objects or not. So this is very hard problem, right? So we don't know how to solve this problem yet. But on the other hand, we can use the bottom-up strategy. That is, we are looking at a pixel, right? We are looking at a pixel belong together if they look similar. All right. So we look at the pixel instead of the whole objects. Okay. So these segmentations can be classified into 3 categories. All right. So semantic segmentations, we only care about the pixel, right? We only care about pixel, which pixel belong to the same categories. All right. But for the instant segmentations, we are also care about how many objects are there. We care about the number of objects. That's what we call instant segmentations. And the panoptic segmentations is the combinations of semantic segmentations and instant segmentation. That is, we care both whether how many objects are there and then what are the pixels that belong to different objects. Okay, so that's what that is the panoptic segmentations. Okay. So if you look at the bigger pictures of image segmentation, we can categorize them into 2 categories. That is, first, traditional methods, which means that there's no learning methods. It's just traditional working with the pixel. So in traditional image segmentation, there would be trace links, region-based, age-based, watershed, and also cluster-based. So these are the traditional methods. All right. On the other hand, we have a learning-based methods. So the learning-based can be classified into another 3 subcategories. That is semantics, instant, and panoptics. All right. So the models that is performing this sort of learning-based segmentation would be, for example, for semantic segmentations, it would be the one that is very popular would be UNet, right? So that's what we're going to learn today, and then we are going to have our hands-on for today. And for the instance segmentations, we have RCNN, which we learned previously, fast RCNN, faster RCNN, and also a mass RCNN. For the panoptic segmentations, there's the models like panoptic FPN, efficient, PS, right? So, however, in the last 2 or 3 years, there's models that can do all of this in a single model that is called segment anything models from Facebook. All right, so it can do all of this segmentation altogether in just one models, right? So let's first look at the classical method. So the classical method would be, here's the list of those classical methods that we can use to perform the image segmentation, right? So for example, we have global thresholds, adaptive threshold, and also we have k-means, meanship, something like that. All right, so you might have a questions, why should I care about the classical methods, right? Why should I jump into a learning-based methods, right? So in some applications, when you trade off between the cost and the time that you spend to develop models between the learning-based and classical methods. So in many cases, classical method would be cheaper, right? For example, this is a project that I worked when I was a researcher. So this is a project that I worked with EGAT, so the electrical generations something. So it is the electrical generation company in Thailand. So they have this very big hybrid solar farm, which is located in northeastern of Thailand, right? So what I want to do here is that, so when you use a solar farm over time, so you need to inspect them whether they are in a working conditions or not. Otherwise, you have to replace it, right? So if you use human to go on this farm, it would take a month because they have to drive a boat and then like walking one by one, and then you have the infrared sensor to spot out whether which solar panels is defected. All right. So what we are doing here is that we are using the drone. All right, we are using drone equipped with infrared cameras as well as the RGB cameras. All right. So why are we using the infrared cameras? Because if there is a short circuit in the solar panels, it's gonna be real hot, right? It's gonna be very hot if you compare it to other areas. As you can see here, there's a very bright spot over here. So that means that solar cell, that solar panels have to be replaced because it's already malfunctions. All right. So if you're assigned to this project, and then you choose to use the deep learning or learning-based methods. So what you have to do is you have to label them, right? You have to like manually label which solar panel is good, which solar panel is bad. So it doesn't work, right? It doesn't work because it takes a lot of time. So what we first do is that we kind of use techniques for classical methods. For example, we perform because when a drone fly, right? So it takes a snapshot, capture one image at a time. So we need to stitch the image all together to create one big image that cover all the solar farm. So we use that stitching methods like we did in a panoramas, similar techniques. So after you stitch them together, and then you perform some sort of lens distortions, right? Because when we are taking the image, there's obviously there's a distortion that happened because of the lens, right? And then after that, we can perform the segmentations by using a classical method here, right? We probably use, for example, a trace shading or something like that. So for example, here, this solar panels is defected. This solar panel, there's a short circuit over here, So this has to be replaced. This has to be replaced. This has to be replaced. This one as well. This one. This is good. This is good. This is good. This is good. So that's how we do. And that's why you need to somehow be aware of the classical methods when you're doing this sort of computer vision applications, right? So because sometimes before we go to a learning-based method, we need a classical method give us some sort of data set or create a graph instead of us as a human to like. So when we are doing a learning-based, what we have to do is that we have to do something like this. You have to draw a rectangle at these locations, all right? And then what you're gonna get from this is an x, y locations of this, and then the width and height of this. So this is where the short circuit happens. And then you're gonna create another sample, This is how a good solar panel looks like. This is how a bad solar panel looks like. So you have to do this manually. So it's impossible for us as a human to do. So when we are talking a very big scale of solar farm like this, right? So you cannot do everything for that. Okay. So that's why we need to know the classical method so that we can apply for this one. So as we start building, collecting more and more data, and then trying to use a classical method to help us label the data so that later we can use those label data as a data set and then train the model later. Yeah. So if we use as a visual characteristic of the pixel, so if we want to perform classifications, what kind of characteristic of the pixel that we can use to perform classifications? I mean, the segmentations or clusterings. So we can look at the brightness, the color, the positions. So this is what we call a direct measures of the pixel. And we can also have a depth, a motions, a textures, and a materials. So this can be computed from the image, right? So that the depth we can also compute, the motions can also compute, textures and material can also compute. So these are the visual characteristic of the pixel that we can use to do the segmentations, right? So for example here, if you want to perform a clustering of this image, right? So what we can do is that the pixel here is in a Euclidean space, right? It's in a Euclidean space. So then if you want to perform segmentations of this image, so this would probably be one segment, right? This is probably one segment. This would probably one segment. And then this would probably another segment. So what we can do is that from the visual characteristic of the pixel, we can convert this pixel in Euclidean space into another space that is RGB space. All right. So what in this example, what we have is that we have the RGB space, and then we map each individual pixel to this space. All right, so this is Euclidean space that is X and Y only. All right, so you can map that so that you can see that from here we can probably find some threshold and then try to group them together, try to group the pixel together, for example, somewhere around there, and then another group over here. All right, so for this space we can create many other higher space. For example, we not only consider RGB, but we also probably can be consider X, Y, and then the depth of each pixel as well. So these are what we call the higher dimensions. All right, going from 2D, all right, into a 3D, 4D, 5D. So we can split that. We can separate. Mhm. All right. So here, what we can do to measure. So after we project each pixel into the RGB coordinates or RGB dimensions, the question is, how can we group this? How can we make a group of this pixel together? What kind of measurement that we can use as a threshold to measure whether this pixel they belong to the same segment of the image? So what we are doing here is that we are using the L2 distance. So we find the sum of square root, sum of difference, all right, sum of square difference between the two pixels. All right. So for example, here we have this pixel. We have this pixel and this pixel. So we compute the distance between the two. If they are smaller than some threshold, we can say that they might belong to the same segment in the image. Okay. So after we do that, we probably get this mini cluster, right? This mini cluster after measure the distance. So we probably get this mini cluster. So we can map it back to the original image, whether which pixel belong to the same cluster, same segment. All right. So this is what we call a segmented image. All right. So that's one way we can do. All right. So that's kind of very easy way to do. Another way we can use a k-means segmentation, right? A k-means segmentations. For example, we have a segment, the given pixel feature distributions into 3 clusters. So how can we do it? So step 1, right? So each dot here is the pixel, features. So the step 1 is that we randomly generate the initial centroid. So these are the space, right? These are the space. These are the group of the pixel. So what we are doing is that we randomly select the initial centroid, anywhere in this space. But so for example, we have 3 clusters. We have 3 clusters here, red, green, and blue, right? So the first centroid of the green is over here, red and blue is over here, right? So the next step, we then create a cluster by assigning each point to the nearest mean. So the centroid, right? This is our centroid, which is the mean of each cluster. So then after that, we are calculating how far they are each point from the centroid, and we assign them to that group. Okay. And then we recompute the mean. All right. So after we assign everything, we recompute the mean for that group. All right. So the mean will move. After we recompute them. All right. So the mean we move. The green one we move from here to here. The red one we move here to here. The blue one we move from here to here. So we keep repeating this step. All right. We keep repeating. So until this is what we get as the final cluster. All right. You got the idea, right? So you just pick any point in the space, and then after that you're trying to assign every point, every pixel to the nearest centroid, and then after that you compute the mean again of that group. So the mean will shift. So right, so the shift, it will move. So you reassign the group again, then you recompute the mean again until you reach this kind of cluster. Okay. So if you look at the pseudocode, we say that given the image with n pixel, let's say 1000 pixel, And then it depends on how many number of cluster we want. So we set k is equal to the number of cluster. And then the task is to find the k cluster. Okay, so for the clustering, we pick any random numbers as a centroid, right? And then after that, for each pixel, we just find whether it's belong to which mean from M1 to MK, and then we assign that to that group. And then we recompute the mean of that assigned pixel. And then after that, we can recompute it, reassign the cluster again, right? Until the mean stop less than some threshold. So what do we mean by less than some threshold? For example, here, if the mean is moving from here, if the mean is moving from here to here, and then the distance between the old ones and the new means, the distance between them, d less than some epsilon. So we are stopped, right? We stop. We don't move again. We don't move the mean. We don't move this mean or the centroid of this group. Yeah. So that is our stoppage criteria. All right. So that's the k-mean segmentations. Any questions?
We have this by hand.
Yeah. So the question would probably be how can we initialize the k, right? So the method one would be we can select any like k random feature point as an initial centroid, right? So if any two that the one that from resample is very close to each other, we just resample. So what do we mean? For example, at the initial step, so this red and blue, they are very close to each other. So we probably might consider resampling this centroid again before we move on. Or another method would be we just use a uniformly distribution means within the range of the distribution. So we have a distributions of this pixel, right? So we know the distributions of that. We probably look at them like a normal distribution, and then we just pick any point with respect to the normal distribution. So we can sample the centroid using a normal distributions. And another one would be the third method would be we perform a k-mean clustering on a subset of a pixel and use the results at the initial mean. So what do we mean by that, right? So let's say that we have a k-means of k is equal to 2, right? K is equal to 2, and then we map this input pixel to the RGB color distributions, right? And then we perform a clustering based on this space. K is equal to 2, right? We based on this color. So this is what we got. K is equal to 2, right? And then if we increase k equal to 3, so this is k is equal to 8. So this is what we got. This is a segmented. So the k here is not fixed. We have to pick it by hand, right? The k over here. It depends on how many segments we want. Okay. And if we increase the k, the number of k, it would give us a better solution. And sometimes, if too much of k, for example, here k is equal to 16, as you can see from here, there are a lot of disjoint region, right? There's a lot of disjoint regions. So instead of just mapping from Euclidean space to RGB, we probably increase the dimensions of this RGB color distributions. So for example, if we map this into RGB space, this is what probably we end up with k is equal to 16. But if we set k is equal to 16, but increase the dimensions of this image, this pixel, by RGB X and Y, so this is a result we got. It's much better result, right? So there are two parameters you have to consider here is the number of Ks and the size or the dimensions of the space that you want to map the pixel value, right? So what is the advantage and disadvantage of K-mean segmentation? So first, K-mean is very simple, fast to compute, and then it's converged to a local minimums. But the con is we need to manually pick the number of cluster, right? And also it's very sensitive to outliers. If we have lots of outlier, so K-mean is very sensitive to that, right? So that's K-mean, right? So next, the mean shift, right? So next, the mean shift. So the mean shift is that we do the same thing. We project the RGB pixel, right? The RGB pixel in Euclidean space into a pixel feature distribution, right? And then after that, we can normalize this one. So if you look at the density of each area here, we can use that density as a peak of each cluster, right? So each peak. So what do I mean by this one? What do I mean by this? So if you look at this one group, and you look at this one group, and you look at this another group, and you look at this another group, right? So as you can see, there are very high density in this area, all right, in the very high density. So this high density area, so this is the number of pixels that fall under these distributions. So if we take this density as the height of the surface, right? So it would probably correspond then to this area, and then this area would be correspondent to some of this area, all right? And then another would be somewhere around here, probably, all right? So each of the hue, so this is what we call hue, right? Because it had a peak. Each of the hue over here, it represents a center of the cluster, right? It represents the center of the cluster. So the question is which pixel belong to this cluster, right? Which pixel belong to this cluster? So what we have to do is that each pixel that climbs steepest hue with its neighbors, this black dot, right? This black dot. So we sample this pixel, and then we can see that each pixel here, it is climbing the steepest hue within its neighbor, right? So the pixel assigned to the hue it's climb, all right? For example, we are picking this sample pixel. So what is climbing is this way, is climbing, because, for example, this pixel probably be somewhere around here, this pixel, right? And then the peak of the hue would be somewhere around here. So if you look at the hue, right? If you look at the hue, this pixel would be climb somewhere here and then climb there, right? So which means that this pixel would belong to this hue because that's what it climbed to, all right? And then if this is another hue, another peak, right? And then we sample the pixel from here, so it would be probably somewhere around here. And then we look at where is this pixel climb to, right? So this pixel climb to this hue, which is climbing to this hue. So we can say that this pixel belong to this cluster, all right? So that's how mean shift is doing.
It's convert to the extract point.
Mm-hmm. Right. So this is after we consider this one, so we're gonna end up with this different cluster. Right. So so how can we find how can we know the pixel climb the hue? How can we know that? So the mean shift is seek for the mode. So what is the mode? We have mode, median, means what is the mode? What is the mode?
The most appears in the,
The most appear?
yes, I mean intense. I mean, if pixels 25 value is the most appear in the array, so it's the mode.
Okay, yeah, that's right. So the mode is the pixel value that appear the most. Okay, that appear very often, most often. Okay, so for example, if you have the value from the pixel 1, 1, 1, 1, 2, 3, 4, 5, 6. So the mode will be 1 because there's 3 ones. All right, 3, 1, only 2, 2. And then 4, 5, 6, only 1 appear there. So the mode will be 1. So the mean shift algorithms, it's 6 for the modes or local maximum for density, right? So what we are going to do first, first we have to set the search windows, how large the space we want to search, right? And then the orange one would be a center of the mass, So next, what we are going to do is that we are going to, so this is our search window, right? So we pick any random numbers. We pick any random pixel over here, all right? And then we calculate what we are going to do. We are going to find the mode within this area. And then we are going to ship the mode to the center of mass over here. So, and then after that, so this is a vector, right? This is a mean shift vector that's where it's moving. If we first start with this point, it is going to move from here to here. And right, and then we are keep repeating the same thing. We are keep repeating, right? We are keep repeating. This is the point, the new point. So then we want to find where to go next. Within this, when consider only this area. All right. So the center of mass means the mode value within that area. So, right. So this is the mode value. So you are moving toward the mode. So we are moving from here to here, yen. Right. And then this is the searching area. We find the mode within this searching area. So that's where we are going to move to. Right. So we keep repeating this until it is converged, which means it stopped. Okay. So let me repeat that again. Maybe some of you are confused. It stopped moving. This center of mass stop moving, or it is the chain, the vector chain, less than some epsilon, less than some threshold, it stop moving. So that's where we know it's already converged. Right. So because if you are at these positions, and then you search at this one, the mode will be this one. The mode will be at the centers of that one because it doesn't move. The most is the one that happened the most, right? So it didn't move at all after that. Right. So for example, if we start from, let me see. So if we randomly start from any pixel, so this is our space that we are care about, right? So we randomly pick any point. So this is the point that we are randomly picking, right? So this is the size of the search window. We have to set this one, and then after that, we are going to count this one. Which one is the one that is happening the most within this one? So that's what we call center of mass. Right. So this one is very dense. This area is very dense, which means the value of pixel fall under this area very much. right? Many pixel. So which means that the point that we are randomly picking here, we have to move to here. We have to move the center to here, right? And then after that, so that's what we move. And then after that, we keep repeating this again from the old one, looking at the search windows and then find the mode again. And then we shift our center of mass to the new positions. Keep repeating this until we converge. So this is the peak. All right. So after we got the peak, so we know that each pixel where it is climbed to, where it is climbed to mean this one is climbing from this to this to this. So which means it belongs to this cluster, it belongs to this cluster, this point that we climb, because the vector, right? So when we calculate the moving, we have the vectors. So the vector tell us where these pixels, if you start from this pixel, where it is being end up with, right? Where it is being end up from here to here. So that's what we call it climbing the hill, because this is a hill.
How
So,
can we find the size of
so it's randomly.
the
It's
cycle? How can you define the size of the window?
you have to trial and errors. Yeah. So this is the algorithm, right? So you set the mi is equal to fi as the initial mean, right? As the initial mean for each pixel. So you keep repeating for each mean. You place the window size w. So this w is you have to try and errors what is work best around the means, and then you compute the centroid. You set the means to the new positions, and then it will stop if the move less than some thresholds. So then you label all the pixels that have the same mode belong to the same cluster. Right. So if you look at this image, all the pixels in here will climb to these positions. Okay, so that's mean shift. Okay, so if we compare the k-mean and mean shift performance, so from the same data, as you can see, the mean shift perform a little bit, I think, perform better in some sense, right? So if you look at the separations between the cluster, mean shift works better. Okay.
That's because you choose k equal 3 when you using k mean.
Yeah.
So you define without that you have only 3
Mhm.
clusters.
So so the drawbacks of the k-mean is that you have to define the number of clusters you are interested in, but for the mean shift you don't have to, right? You don't have to define like how many clusters are going to be there. If you find the peak, how many peak are there? That's equal to the number of clusters we have. Okay. So here's the result of using k-mean of 16 and the mean shift with 21. Yeah. So if you look at this one, the mean shift will look much better here. Yeah. So the advantage of the mean shift, like I said, so there's no initialization required, so you don't have to define the number of cluster. All right. And it's also flexible in the numbers and shape of the regions, and it's very robust to the outliers, right? But the con is computational expensive, right? The con is very yeah, and then the selections of window size, we have to trial and errors. What is the window size that is optimal for our problems, right? So that's the mean shift. So that's the classical methods. Any questions?
So in practical,
So in case that sorry, echo. So that you're gonna train, but how the segment or thing is still like it's like I mean we don't have proud truth for this, right? Do we have?
No, there's no
No
ground
proud
truth.
truth. It's like a segmentation in
Yeah.
like unsupervised things.
You
So
can say you cannot say unsupervised because it's not learning. It's not learning.
that is sorry, it's not.
It's classical method. It just work purely on the algorithm, so there's no learning. Yeah.
Okay.
thì tức là mình phải
So yeah.
Okay, I already asked.
Okay. So what is what is the question?
Someone
rely
Uh-huh.
Hey, you
How to
we see
apply the different why choosing k-mean but not in segmentation or because
Oh, okay. Okay. So if you know for sure how many clusters are going to be there, you can use k-mean. You can use k-mean for that because it will give you exact number of the cluster. Right? If you know for sure that you want 16 cluster, that's exactly the number you want. No more, no less than that. You want that one, you choose k-mean. But if your application is kind of flexible, you don't know how many clusters are going to be there. You just mean to. So it will give you a flexibility whether it probably could be 16 cluster, it could be 10 cluster, or sometimes it would probably be 20 cluster. It depends on the data. So if you want exactly number of cluster like 16, you go with k-mean. Right? If you are flexible, you're flexible. You don't care how many clusters are there. You just go with meanship. Meanship going to work better for flexible number of clusters. Yeah. It will take longer. Yeah, it will take longer for the meanship. All right. So that's the classical method. All right. So now we are going to move our gear to learning-based methods. Right. So now we are going to use machine learning or deep learning models to perform segmentations, right? So like I mentioned that we have 3 different subcategories for the learning-based methods. So let's first look at semantic segmentations. Right, semantic segmentations, we just purely care about the pixel only, right? So in semantic segmentations, right? In semantic segmentations, we label each pixel in the image with category labels. Right? No differentiation between instances. So what do I mean by that? So we just want to differentiate between whether the pixel belong to the sky, pixel belong to the tree, pixel belong to the cat, pixel belong to the glasses. But in the case of semantic segmentation, we don't care how many cows are there. So we just, if they belong to the cow, we just assign them to the cow. All right. But if in instance segmentations, these 2 cows have to be belong to different cluster or different segment, instance segmentations, because we care about instance. We care about the object, individual objects. All right, but in semantic segmentations, we don't care about individual objects. But if they are the same objects, they are assigned the same class, same content. Right. So the very simple way to do is that we can do sliding windows. All right, we can do sliding windows. For example, you can define a sliding windows. For example, you can define this size of windows, and then try to extract, and then you take out these patches, right? You take out these patches pass it into the CNN and see whether these patches belong to which objects, right? So when training this kind of models, you have to define how many classes, how many objects you are interested in, right? For example, you are interested in 20 classes, so which means that your CNN will predict 20 classes, right? 20 classes would be, for example, would be a cow, a glasses, a trees, the sky, something like that. So these are the classes that you are interested in. Okay. So for example, here, if we take this, if we take a sliding windows, we slide it, and then we keep sliding like that. And then if we end up at this location, this is the patch that we got. And then we pass this patch into the neural network, right? The models, it would probably predict that this entire patch belong to the classes, right? Because if you look at the image here, the classes dominate the number of pixels belong to the classes dominate the other classes. Right, so that's the sliding windows, but the problem is that it's very inefficient, right? It's very inefficient because it depends on how big or how small these sliding windows. You have to keep sliding and then pass each and individuals of those patches into the network. So you have to run to many times. All right, so that is very, yeah, that is very inefficient for that one. But it easy to implement, but not efficient. So another one of the popular semantic segmentation network would be FCN, which is fully convolutional network. So it is purely, so the thing, there's no innovations much here. So you just pass in the image, all right? You just pass into numbers of convolutional layers, and then you output the layers with the same width and height of the image, right? With the same width and height. The difference here is that if you look at the image, right, it has 3 channels, but at the end here, the result, the predictions here, there's no channels. So the predicted result needs only match the size of the input here. And then for each pixel here, we just predict whether it belongs to class 1, class 2, class 3, class 4. That's it. All right. So there's nothing fancy here. Just pass it into the numbers of convolutional layers. And then for the loss function, you just compute the cost entropy per pixel, right? Because you just care about whether it is correctly classified as the ground truth pixel or not. So what is the drawback of these models? Anyone can spot the problem with this model?
Drawback for segmented.
Mm-hmm. What is the drawback of these models? So for the sliding windows, right, we are saying that it is very inefficient, right? Because we have to pass these windows into the network many times, right? So that will consume a lot of computational power. And after that, there's another paper come out named FCN, that is, you just pass the entire image instead of just a patch. You pass the entire image into layers of convolutional layers, and then you get the result. So what is the drawback of these models?
Details. They lost the details. No.
They can be detailed because the prediction is for each and every pixel, right? Yeah, it is very detailed prediction.
No, it's convolution is more detailed already.
So the problem is that if you remember the receptive field, if you remember that, so for the for the neurons here to see the entire image, for a single neuron in these layers to see the entire image, right? To see the entire image. That's what we call receptive field. So for example, if we use 3x3 filters, these layers, right? You need 2 layers with 3x3 strike 1 for this neuron to see a 5x5 layer receptive field. Do you guys remember receptive field?
Yeah.
So receptive fields with respect to each layers is the how large the areas of the input that this neuron in this layer see, right? So the problem is that if you have a very large image, which means that you need this many layers
Oh,
to get that this neuron at the very last layer going to see all the pixel in the image, right? So which means that you need lots of layers. It depends on the size of the input, so you need lots of layers. So when you have lots of layers, which means that you need a lot of computational power, right? Because you have many layers, the number of parameters goes up with the number of layers, right? So that's the problem with this models. So if you use higher resolution image, you're gonna need like many layers of convolutional layers. So to solve that, what we can do is that we can just do like we can do just like the traditional CNN. Okay, the traditional CNN means that when we goes from very high resolutions, when we perform the convolutions, we also perform a downsampling by using max pooling, without sampling using max pooling, or without sampling using kernels without paddings, right? So that's how we without sampling. For example, if you have the image of 5x5 and then you convolve with the filter 3x3, you're going to end up with 2x2, right? So without any padding, you're going to end up from 5x5 to 2x2. That's how you downsampling with convolutions. Or if you perform a paddings, you can downsampling using the max pooling layers. All right. So to reduce the number of layers that require for the neurons at the deepest layers to see the entire image, so what we can do is we perform a downsampling, right? We perform a downsampling so that the neuron at this location, the number of layer that is requires for this neuron to see the entire image is reduced, right? And then after that, since the semantic segmentations, what we need is that we need the output, we need the resolutions of the output to match with the input, So if without sampling, we need to upsample them so that the final result will match the dimensions of the input. So that's why we have the upsampling. So without sampling and then we upsampling, right? For example, we would probably go from 448 by 448, and then at the end of here, at this layer, we probably like 20 by 20, right? So then after that, we upsampling from 20 by 20 back to 448, by 448, so that this match with the input, so that each pixel is being classified as whether they belong to which segment or which class of objects of our interest. So for the downsampling, we can use convolutional layers with stride or with paddings. But for the upsampling, right? For the upsampling, how can we upsampling from the feature maps to match the resolutions of the input layers? So these are the methods that we can use as the upsampling methods. right? So from bed of nails, nearest neighbors, bilinear interpolations, bicubics, max unpooling, or learnable upsampling. So let me just go through this. So the best bed of nails. So this is the input, right? This is the input. I mean, the input in the sense means that, so this is your input image. You're downsampling it, and then you're gonna upsampling. So the input means the thing here, right? So you're already downsampling it. This input is mean this one. So you want to upsampling them now, okay? So you want to go from 2 by 2 to 4 by 4. So what you can do is that you just map, you create a windows of output of 4 by 4, and then you just put this into the upper corners of each region, and the rest will be 0. All right, so that's the bed of nail. And for the nearest neighbor is nothing but you need 4 by 4. You just put everything in each quarter, right? You put everything, you divide it into 4 regions, and then copy everything from here to here. All right, so that's the nearest neighbors. So that's 2 ways you can do. So the other way you can do is bilinear interpolations. So the bilinear interpolation means that you want to go from 2 by 2 to 4 by 4. So what you're going to do is that you're going to place the dot, the grid over here, right? You are going to place a grid of 4 by 4 or 4 by 4 over this region, right? So which means that 4 of the dot will be in this quarter, and 4 of the dots will be in these quarters, and 4 in this quarter, and 4 in these quarters. So you want to map this dot, each of them into this location, right? Because the final will be 4 by 4. And then, so we know for sure this dot is going to be 1 because we place it exactly at 1. But this dot, we don't know what is the value of that. So what we are going to do is we are going to perform a bilinear interpolations between know the distance between this 1 and this 1. And then we can calculate the distance between 2 and these positions, right? So we can perform a bilinear. So we're going to end up with 1.25 over here. And then this one, 1.27, and then 2. Right, so that's how you calculate. You perform a bilinear interpolations. So you do this for each and every grid, right? So that's the bilinear interpolations. And for the bicubic interpolations, it's very similar, right? You are using 3 closest neighbors. What do I mean by 3 closest neighbors? So for example, this point, what is the 3 closest neighbor of this point? The 3 closest neighbor would be this one, right? This one and this one, right? And then you calculate the combinations of, you calculate the distance from here to here, distance from here to here, distance from here to here. And then you end up, it's very similar to the bilinear, but instead of 2, you use 3. So that's the bicubic interpolations. And the other one, so as we know, we can downsampling using max pooling. And then the other one would be the opposite of max pooling, would be max unpooling, right? So how can we do the max unpooling, right? So when we are taking the max pooling, going from here to here, we are not only taking the value, but we are also remember the positions, which position we are taking this 5 from. So this one would be x is equal to 2, y is equal to 2, right? So this one. So when we do a max unpooling, so we know for sure where to put this image. I mean, where to put this value back. That is at the location of x equal to 2 and y equal to 2. So we just place this into this cell, and the rest will be 0. Right. So that's how we do a max unpooling. All right, and the other one, so this is what we call a learnable the learnable unpooling, right? The learnable unpooling. So we call it the transport convolutions, right? We call transport convolutions. So for example, we have the input of 4x4, right? We have the input of 4x4. So when we're doing the convolutions, we are doing convolutions. So let's say that we have a 3x3, strike one, pad one. So this is what we end up with. So we're gonna get the same dimensions, right? Going from 4x4 to 4x4 with this configurations, right? So if you are padding one, so you're gonna get the same dimensions. And so you just, this is how we do the evolution. You just keep doing that. And then if we do the strike is equal to 2, so we can downsample from 4x4 to 2x2, right? So that's just a normal convolutions, right? So how do we do the transport of that, which means the opposite of convolutions? So what we can do is that, so remember that we want to unpooling, right? We want to upsampling. So we are going from 2x2 to 4x4. So this is what we call a convolution transport. So what we are going to do is that we are placing this. So we initialize the output of 4x4. All right. And then we initialize the filters. All right. This is our filters. This is our filters of 3x3. Okay. So the value in each grid will be random. Okay. So the value in each grid here will be random. So it's learnable here. So the model is going to learn what is the value of these filters. All right. So what we are going to do is that first, we are going to initialize the output 4x4, and then with the filters of 3x3, okay? With the filter of 3x3, and then after, what we are going to do is we are going to multiply this value. Let's say that we have this 2, 3, 4, 5. That is the value of these feature maps. All right, and then this is the value. Let's say that 0.5, 1, 0.5, 1, 0.5, 0.5 over here, 0.5 over here, and 1 over here. So these are 0.5, these are 0.5, these are 1, just a dummy number. All right. So what we are going to do is that we are going to multiply each and every value in these filters with this value from our feature maps. All right. So we multiply that and then we sum them up. All right. We multiply and sum them up. What is the value of these locations? If we have a filters of 3x3, and then this one will be 0.5, this one will be 0.5, this one or 1. So what is the value of this? The value of this. One, 2, 2, right? 3 plus 6, 3, 6, 18, isn't it? 3, 6, 12, right? Because this is 6, this is 3, this is 3, so we got 12. So after multiplying this and then you got it? 12. So let me do that again. So this is filter, right? So this is filters. So the filter is randomly initialized. And then the value in these filters, this location 0.5, 0.5, It's random, we can put anything. So probably this one 1, and then this one 0.5, 0.5, and 0.5. Okay, so this is this one. So we want to go from 2 by 2 to 4 by 4. So what we are going to do is that we are going to, let's say this one is 2, 3, 4, 5. This is the value of this feature map. So what we are going to do is that we want to find the value to be assigned to this location, each and every location in here. Okay. So what we have to do is that we are snapping the kernels into this location, for this position. So to get the value of this one, you first multiply this value to each and every element in this matrix, in these filters. So you multiply 2 with each of this one, you're going to get 1, 1, 1, and 2, 2, 2, 1, 1, 1, right? So you're going to get 12. So you assign this value 12 in here. Okay. And then you move to the next one. It's just like we do the filters. So you move, you strike. So you move that, you strike that one, you find again. You get it? Okay. And then you you get from here, you get this 12, and then next this one, these elements, you are going to, so here we are defining that we are going to strike for 2, right? We are going to strike for 2, which means that this is the strike 2, right? This is the strike 2, 1, 2. All right, so next. No, let me see. I think there's something wrong here. Oh, no. Sorry. So we are not summing up. So what we have to do is that, so for each filters value here. Okay, let's say that we randomly, right? We random 0.5, 0.5, 0.5, and 1, 1, 1, 0.5, and this one 0.5. So it's 2, 3, 4, 5. We first multiply each and every one of this to 2. So this will become 1, 1, 1, and then this will come 2, 2, 2. This will be 1, 1, 1. Right? So this location we have a value of 2. This location now we have a value of 1. This location now we have a value of 1. This location we now have a value of 2. And this one is out of the region, so we just ignore it. Okay. All right. So next we strike to we move to pixel. So we move to pixel, right? So currently we are getting 2, 2, 1, 1, right? And then we are doing the same thing. So this is 3, right? So we are multiplying this 3. This is going to be 1.5. Let me change the color. This is going to be 1.5. This is going to be 1.5. This is going to be 1.5. This is going to be 3, 3, 3, 3, and 1.5. 1.5, 1.5. So at this area you get 3, 1.5. But this area you have 2 numbers, 1 and 1.5. So you're gonna sum them up. You get 2, 2.5, 2.5. You keep repeating this for all elements. All right. So that's how you go from 2 by 2 to 4 by 4 using what we call transpose convolution.
Cái chỗ nào nó đè lên nhau là
The what? The width? You mean this one or this one? The width of filters or the width of the output? How do we define of what this one?
Give the canal the sign of the signal, why is
2 by 2 or 3 by 3?
yes, the canal, why?
This canal.
This sign.
So you can define others. You can define other value. You can define 5 by 5, 3 by 3. If you define 5 by 5, it's gonna be this much. It can be 5 by 5.
For this example is the 3 by 3.
3 by
and
3,
the
yeah.
try is 2.
Yeah.
You want to know
Mhm.
why is the canal is 3 by 3 and the try is 2.
It is your choice whether the value in the kernels it's random. Yeah, it's random. It's just like when you do a convolution, right? When you do convolutions, because we want the model to learn this value. We want the models to learn these parameters. So we randomly initialize to 0.5, 0.5, 1, 1, 1, 1. And then we want the model to learn this value. What is the optimal value for what is the optimum coefficients of this kernel? We want the model to learn that, right? So when it do a back propagation, this value will be adjusted. Yeah, so it's very similar when we do a convolution, but we are just doing the opposite. This is what we call a learnable unpooling, and the learnable upsampling.
But the convolution is
The convolution is performed downsampling.
and opposite is the upsampling.
Yeah.
So the original maybe become not original.
So the value. So when we are talking about the values, or we call in the filters. So that the filters here, the coefficients or the value here is what we call modules parameters, or the weight of the modules. So this is the weight of the modules. All right. The value in each filters, that's what we call a weight of the modules. The weight of the modules. All right. And then this weight are randomly initialized at the beginning of the training. Right. So as the training goes on, epoch by epoch by epoch. All right. For one epoch, we are going to compute the gradients. All right. We compute the gradients, and then we are going to adjust the value in these filters, or we call the model parameter, or the weight of the modules. We're going to adjust it. So this is similarly, this one is randomly initialized as well, and then it will be adjusted as we train the models. So maybe finally it wouldn't be 0.5. It would be somewhere, for example, 0.9, something like that. It could be any value.
So how the model know to stop?
So the how the model know to stop when to stop adjusting, right?
Yeah.
So it depends on number of epochs. All right. So when you train the models, that the loss goes down, and then for example, you are saying that if the loss go below 0.1, you stop training the models. That's when these parameters stop. That's when this parameter stop updating. All right. So or if training for 100 epochs, so after 100, that's where the model stop update the parameters. As long as you are training the models, this value will get updated. Like say 1,000 epochs, it will update 1,000 times. Yeah. So if the question is how do we know when to stop, it's trial and errors. So it depends on how low the loss you want, or how many epoch you want. That's where you want to stop. Or for example, you say that if the models have the precisions or have the accuracy above 90%, just stop.
Yes.
So that's where you are stopping updating that value. Yeah. So yeah, you keep repeating this process. So that's how the transpose convolution works. So these are just the example of 1D. So it's just like what I described. All right. So probably maybe you will see these different terms that describe the same operations. For example, some people call deconvolutions, some people call up convolutions. Yeah, but probably the best name would be transport, because it's just the opposite of the convolutions. It's just a matter of the name, right? All right. So that's how we can perform downsampling and upsampling, and then we can use this fully convolutional network to perform the semantic segmentations. Okay, so one of the example of the models that is using these techniques, and it is very popular, and it has been used in many kind of segmentations, or even like biomedical applications or medical applications, would be UNet, right? So UNet did exactly like that. It has the downsampling size, which is what we call contractive path, right? We just feed in the input, perform some convolutions, downsampling, perform some convolution, downsampling, until we get into this is what we call a bottleneck, right? This is what we call a bottleneck, and then we upsampling, or we call expansive path up, and then the thing that so the thing we have to note is that when we are working with the deep learning, the deeper you go, the more information loss between the layers, right? So the very end layers would probably forget about informations, the low level informations of the image. So how can we tackle that problem? Is two ways. So one way is to do something like ResNet did. They have a skip connections. And UNet, they have a very similar idea, using a skip connections, but skip by adding special informations with some sort of different resolutions. All right. So there's the skip connections to match from this upsampling and downsampling and upsampling. So you just added this feature map to this feature map, just added this feature map to this feature map. So just to add the information that has been lost during this downsampling process, to add it back, so that these layers, they are aware of the low level features of the image. So that is a reason for that. Okay.
Question.
Yep.
When reading about this one, some terms they use in this guy we call encoder parts on the left hand side and decoder part on the right hand side. Is this a same concept, or is it different?
Yeah, you can say that, because if you look at the size of the model, you can look at it something like this, and then you have a bottleneck here, and then you have expansive path.
Yeah.
So if you look at this model, it looks like the autoencoders, right? It looks like autoencoders. So that's why they call this, probably sometimes they call this encoder, and this is decoders. Yeah.
Okay.
It's just a matter of terms. Yeah.
Yeah, is just make sure that it's a matter of terms. Don't mix. I mean, the concept different things. Okay.
So that's UNet for semantic segmentation. Okay. So for semantic segmentations, we are giving per pixel label, right? So we don't care about how many instances are there, even though like the cow, there are 2 cows, but we don't care. We just care whether the pixel belong to the cow or not. So So that if you want to address these problems, we want the models to be able to perform segmentations as well as to perform the object detections. So that's what bring us to instant segmentations. Right? So the instant segmentations in computer visions, we are talking about things and stuff. Okay, things is the objects category that can be separated into different instances. There is cat, car, persons, dog, car, something like that. So that's what we call things. And stuff would be the thing that cannot be separate, like the sky, the glasses, the waters, the trees. So this is what we call stuff. Okay. So the object detections, right? The object detections in object detection, we only care about things, where it is, right? Because we only care about where it is and then what it is. We care about things. For the semantic segmentation, we care both about things and stuff, right? We care about things and stuff. So that's semantic segmentations. And next is the instant segmentations, right? So instant segmentations here, we are detecting all the objects in the image and then identify the pixel that belong to each object. So we care about only things here. We don't care about stuff, right? Stuff mean we don't care about the glasses, we don't care about the trees, we don't care about the sky, all right? So the approach is that we first perform the object detections and then predict a segmentation mask for each object, right? Because instant segmentation, we only care about things, okay? So to perform instant segmentation, we can reuse the faster RCNN for object detections. And then after that, we can use a mask prediction, because as I mentioned that to perform instant segmentation, we can first do object detections to get the locations of the objects, and then grab that regions and then just perform segmentation later, right? So that's why we can reuse a fast RCNN, and then we are adding the mask prediction, right? We're adding another branch of the models to predict a mask. So that what it does is just nothing but the segmentations within that region, within that bounding box. Right? There's nothing fancy here. Right. So what you can do is basically you just maybe reuse the faster RCNN, right? You pass this into the models, and then you get feature maps, and then after that you can perform another convolution to perform a predictions of the mask. That's it. Right. It's very, very much like the faster RCNN. You detected the objects and then grab the regions or the feature maps within the regions of interest, and then pass it into another convolutional neural networks, and then predict per pixel, right? Predict per pixel whether which pixel within this bounding box, within this bounding box, which pixel belong to an object, which pixel not belong to an object, right? So yeah, that's instant segmentation. Right, this is the example of mass RCNN, right? So for example, if we feed this image into the mass RCNN, it would probably detect this area, it would probably detect this object, all right? And then we grab these regions, pass it into another CNN, and then this is what the final result looks like. So the model is just predicting whether which pixel belong to an object, and then which pixel not belong to the objects. All right. For example, here we are having this. So as you can see, for the same object, we could have different size. We could have different size of the bounding box, right? So this is the same chair, but it had different size of the bounding box. And this is the same as the person. It also has, I think this is not a person. This is probably a bed. This bounding box is for the bed. This bounding box is for a child.
Doctor, question
Mhm.
again.
Yeah.
I just want to like I have a image. I want to label the mask by myself, maybe 100 of them, let's say like that. So which tool should I do? I mean, yes, something like that. Let's say I want to label this chair as the mask for the segmentation, and I have the BNG or JPEG. I want to do the like a binary mask, like black and white, right? So I want to manual by myself
Okay.
to create the raw truth for that 100 pictures. So
Yeah.
what tools and what technique should I do?
So if you want to do this manually by yourself, there's a tool labeling tool from Stanford. Let me think. I don't remember the name. CV2 something. Let me do this. I used to use these labeling tools. I used to use this one, Stanford. So you can use Label Studio, right? So I used to use this one. So you can use Label Studio, and then you can choose either which format you want it to output, because when you are doing segmentations and the object detection, there are a varieties of there are a variety of formats that you want to use. For example, a Pascal format, different YOLO formats. They are different. They are doing the same applications, but they encode the data differently. So you can choose the format output. Okay, so this is Label Studio. This is one, and another one would be, I don't remember the name. You can use label image here. Here's one, and yeah, I'm not sure whether RoboFlow is free or not, but Label Studio, of course, is free, and then label image it's become Label Studio. Yeah, you just go to Label Studio.
So
Yeah.
Label Studio is free.
Okay.
Okay.
And there's another one, but from my experience, this one is the best for free. But this one from Stanford, I don't remember the name. Let me see. Label box. No, not this one. I'll file you later. I don't remember the name.
Yeah,
but
no
this,
worries. Yes. Thank you.
but this one can be used for sure. And it's kind of good. This one, Label Studio.
Need to watch
Watch
that tutorial how to do the Label Studio.
But it's very label intensive. Okay. So if you guys haven't heard of Scale AI that Facebook just bought them recently for $1 billion. So that's what Scale AI does. Just provide the data labeling services. So they probably hand the service to a country like us, a country like India. So because we have a cheap labors, so then they just pay like you label 1,000 images, you probably get paid for like $10, something like that. Okay, so it's very labor intensive for this one. Okay, so here's the result of Mash RCNN that performed the instant segmentations. As you can see, it performed the object detection first and then do the segmentation later. All right, and the panoptic segmentation is nothing but the combinations of the two, right? So we are interested in both things and stuff. All right, for things, For things categories, we also separate them into an instance. So that's the panoptic segmentation. It's just a combinations of semantic segmentation and instance segmentations. All right. So here's the example of panoptic segmentation using the panoptic features pyramid networks. So as you can see, it performs both semantics and instance segmentations. We know what and where the object is, and then we know what is the background. So yeah, that's the panoptic segmentation. So basically, the self-driving car would perform the panoptic segmentations. Right? It's not just perform instance segmentation, but panoptic segmentations. Right. All right. So I think this is it for image segmentations, both for classical and learning-based methods. So any further questions? All right, if you don't have any question, let's take 8 minutes break, and then I'll walk you through the unit and some sort of different traditional methods, segmentations. All right, let's come back at 3.
Một giấy này anh phải đi tất cả giấy.
Đúng rồi, cái YOLO ấy, cái quan trọng nhất cái bounding box, cái thực bao nó sẽ có là cơ sở bao max. Hai tay đấy. Xem các cái chụp là gì thôi, cái label.
Very special. Yeah, we have that in Thailand as well, but it's too sweet. Really? Yeah.
It's the dragon. Đúng nhỉ? And this one you have, I think, in Thailand.
Bangkok.
Oh, right.
Yeah.
Oh, Thailand have this?
Yeah.
Yeah.
Sao miền Nam không
Việt Nam có cái này nhỉ?
Miền Nam có nhãn không hả Khoa?
It's also yeah.
Oh, this one I think is you have in Thailand.
Yeah.
Miền Nam có phải không có đâu.
Ở miền Nam là thì cũng phải.
Thì xưa quen một đứa trong miền Nam rồi bảo gửi đến mùa lại thì được
Chủ yếu là nhận diện đối tượng thôi. Này không?
Cái một step đúng không? Để nó nhanh đúng không?
Còn cái phim với cái stop thì nó có cái đéo gì đâu, tức là chốt lại là cái bầu trời này là stop, bởi vì mày không thể chia ra là stop 1, stop 2, tức là bầu trời số 1, bầu trời số 2 được. Nhưng mà chó kiểu rơi gọi là rơi đấy, kiểu còn chó với mèo như là thinh rồi.
như chụp ảnh một bầy cứu đấy rồi một bầy chào
Bây giờ chúng ta ứng dụng đấy vào trong mấy cái trong nông nghiệp ấy, đếm có bao nhiêu việc.
Còn về bản chất thì tất cả cơ sở dữ liệu nó là hình ảnh thế này, cơ sở dữ liệu nó là con số nữa.
Viết thuốc đi, nói nhiều quá.
Ồ, bật quà bật mic à?
Qua tài trợ đi để chiều nay anh em moi thêm thông tin từ thầy à?
Rồi làm
bảo
được
này.
nhiêu hay bấy nhiêu.
Khoa ơi,
Sao?
thầy tí gạ thầy cho thi dùng máy tính rồi dùng internet để cho cả hỏi AI luôn nhá, được không?
Không. Anh
Không
muốn
phải
làm gì cũng được
Không,
hết
cũng
á.
được nhá, chứ không thi
Anh
viết.
muốn gì em chịu theo đó, em dễ mà.
Không phải em thì giỏi rồi, nhưng mà còn những anh em khác ấy chứ không phải mình
Em cũng giống anh thôi chứ khác gì. Code chỗ này nó như một cái đám rừng chứ đâu phải gì kiểu hồi xưa nữa.
Thì bây giờ học computer vision mà thi viết thì ra giấy thì chết.
Thôi chiều nay sẽ
Rồi chiều nay anh nghĩ là thầy cứ 3 cốc là đổi đề, yên tâm. Đổi hình thức.
Em mệt lắm luôn nhưng mà em sẽ bỏ sức
Ừ.
thôi em bỏ tiền.
Chứ con Peter Vision mà lại cứ thi tiếp
Nếu mà không được thầy thì qua tài trợ quả chiều nhỉ? Có nhỉ?
Em phải bỏ sức
Hả?
rồi.
tức là
Sao?
ý thằng Nam nó bảo em tài trợ đi để bọn anh còn triển.
Tài
À,
trợ nữa hả?
Lớp trưởng
Mẹ,
hy sinh.
trên răng với dái có cái mẹ gì anh?
Thằng Việt nó đang bảo là nó sẽ hy sinh cái thân thể của nó rồi.
Thế chú
Thôi,
thu
thôi,
phí
thôi, thôi, thôi.
chiều nay anh cố gắng.
Đang ở headquarter mà cứ đòi xin mà trung ương ở trung ương mà cứ đòi xin tiền cái địa phương thế nào?
Trung ương là ngoại thành thôi. Có anh Hoàng Anh ngoại thành thôi. Cái quán bia nào người ta
Tuần này nào
nào bia đây.
không phải ngày nào.
Nhiều. Say lâu hồi. Trên đấy thì chỗ anh nhiều.
Thực tế em nghĩ nhậu rồi.
All right, so let's start with the lab of traditional segmentations. So I'll walk you through a little bit of how can we do a segmentation using classical methods. Okay, so I already posted this lab. I believe it's lab number 10. Let me see. Is it lab number 10? Yeah, it's the lab number 10. So you can grab that and then open this Colab. Okay. So maybe this is nothing, just run to connect the Google Drive. Okay. And then we load some dependency. So here we are going to use the OpenCV and then scikit image and PIL as well. And so we are going to plot a visualization using a Matplotlib. Right. So connected. So maybe let's just, here's nothing, but we're just trying to visualize the image. Okay, so yeah. So now let's read in the some image. So I have the image in these folders. So I'm not sure. I think I shared this to you guys, right? So you're gonna have in these folders, you're gonna have one Colab and one photos that contain the image that we are going to use. Okay, and then we just grab that from that. So read in the image. So it said failed. So what did I do wrong? So where am I? Okay. So I need to switch to this CD. So you need to switch the working directory, right? So otherwise it won't be able to find this. So if you look at this PWD, so this is the working directory, but my data is in these folders, so I need to change to that. So I need to run this command, change to my drive, and then to what is it, code, and then traditional segmentations. All right, so I change this, and then let's see the working directory. All right, so that's my working directory. Right, so now let's just load in the image. It should work. Yeah, so yeah, so now we're loading in the image. So let me see what I'm doing here. All right, so we just try to read in the image. All right, so basically when you read in the image, it will turn the image into the channel of what? Blue, green, and red, right? So that's why that's why this image is like doing it in a blue channel first, right? So if you want to get the same image as the original, this is the original, right? So we have to convert the blue, green, and red to red, green, and blue, right? So that's what we did here. And this one is nothing but just to make the visualization either vertical or horizontal. Okay. So let's first trying a very basic treasuring method. I think we already did this in very first lecture, right? Just setting the threshold here, right? When we did, if I remember correctly, when we did the edge detections, I think we already used this kind of threshold, right? For example, if I go through again, so this is a simple treasuring, right? So you specify the image, and then this is the range of the pixel, and then what kind of treasuring that you want to do. This is what we do. We want to do the binary image. This is what we do. We want to do the opposite. All right. So in this binary image, we want to suppress the pixel that is below 150. All right. And then this one is the opposite one. And this is the adaptive treasuring, right? So we have this sort of treasuring and then criteria that what we want to do, right? So this is what we end up with, different types of threshold. This is the what is it? The normal simple treasuring, right? This one, and this one is the inverse binary treasuring, and then this one is the adaptive treasuring. Okay, and I think this is another types of binary, treasure. It's called Otsu binarizations, right? It's just another types of algorithm that we can use to perform the treasuring, right? So we use the same functions, right? cb.threshold, and then here, instead of just binary, we also added another algorithm to perform the threshold algorithm, right? So we plus threshold Otsu here as a criteria, okay, instead of just binary. What So now what I want to do is I want to demonstrate the meanship, right? So the meanship here, we are going to use the functions from scikit-learn, all right? So we have we import min-max scalars to normalize the data, and then we also using the meanship, which is a clustering algorithm in sklearn, and then we want to estimate the bandwidth as well. So we import that, and then we read in the image, convert the color, and then resize it beside the image. All right. So as you might know that, as you might notice that from the lecture, right? So the meanship take a lot of computational powers. So to avoid that, we need to resize the resolution of the image. So that's why we did that resize here. Okay. So we do the resize here, and then let's see the shape. So we have, so we do a resizing, right? We do a resizing, and then what we are doing here is that, so normally the image will be channels multiplied with width and height of the image, right? So now what we are doing is that we convert the three dimensional matrix, right? Channels and then width and height. So we convert that into 2D, which is we combine the width and height into one numbers, and then keep the three as channels together. So that this is the RGB. So what we have here is that what we have here. So basically, our image will be something like this, right? And then we can look at 3D, three-dimensional data with height and channels, right? With height and channels. So what we are going to do is that we are going to convert this into a three over here, right? We are going to convert a three. How do I draw this? So we are converting this into 3 with the length of 8, 1, and 900. Okay, this is the size of it. So 3 height, and then 81,000 width over here. So going from 3D to 2D, right? So that's what we did here. and then we convert every pixel value to float. Okay, and then what we are doing here is that, so we are going to normalize. So the pixel value will go from 0 to 255, right? 0 to 255 for each channels RGB. So here we are going to normalize the image into the range of 0 and 1. Right, so 255 will be 1 and 0 will be 0. So we are going to normalize that one. So that's why we are using a min-max scaler to normalize the data. Right. And here to calculate the mean shift, right? So one thing that we need is we need to have a bandwidth. All right, we need to have a bandwidth. So we just use this estimate bandwidth over here, and then we feed in this normalized image, and then specify the quartile, right? The numbers of the 4% of the pixel in the image. What is this warning me? Okay. So as you can see here, when it is estimating the bandwidth, it takes quite some time to do. So after we get the bandwidth, so then we can use that to apply for the mean shift. Yeah, okay. So then we can use that bandwidth to apply for the mean shift. So let's look at this documentations. So so now let's see how many label we have. So these are the number of cluster, right? So after it's calculate, after we perform the mean shift, so we can extract the number of cluster by using this these functions dot cluster underscore center underscore. So this is the centers of each cluster. So this is how many cluster we have after we perform a mean shift. Okay, and then if we plot that, all right, if we plot this one, this is the segmented image, right? So we have, I don't know how many, maybe probably some 10 or 12 cluster, right? We probably have a 10 or 12 cluster over here, right? So that that's how you can do the. So here, what we are doing is that we are reshaping, right? So reshaping means that we are going back from 2D to 3D, right? Because here we have 2D, so we are going back to 3D. So here we are going back to 3D. That is the image size, right? So we are going to match it back to the image size. So the image size would be probably what is it? I think 3 by something by W by H something. Yeah. So this is, we're going back from 2D here to 3D here. Right. So that's what we call reshape over here. So that's how the mean shift works. Okay. And let me just skip the watershed base over here to the k-means, right? To perform the k-means, first let's just load the same image, and then we're going to convert 3D to 2D again here. Then let's print out. So this is what it looks like when you go from 3D to 2D. So this is 2D, right? So it is 3. This is 3 from here, and then it is 81,000 something over here, right? And then for the k-mean, this is the criteria, right? That So in k-means, we want to specify when to stop, right? When to stop searching. So that is the epsilon criteria, epsilon here. Right, so we specify this is the maximum iterations and this is the epsilon. All right. And we say that we want to have four cluster, and then we want to attempt for 10 times. And then you just call k-means over here, input the image, the 2D image, and then the number of cluster, the criteria, the attempt, and then I don't remember this one, k-mean PP centers. What is k-mean PP centers? Yes. And then this is the center. I think this is the center. So the k-mean will return 3 parameters: the centers, the labels, and the result. Right? We convert the centers. So we convert is to unsigned integers. So because probably this center would probably be in some sort of a negative value. So we convert it into unsigned integers. And then for the labels, we just flatten it out from the centers. Right, and then we just reshape it back to the original shape. Right. So if you run that, so that's how you get from the k-mean. So we specify 4. Maybe you can try to change, for example, if I'm trying to change that to 10, right? 10. Yeah, so as you can see that there are 10 cluster in the 10 cluster in this image. Or we probably maybe down to 2. Yeah, these are the two cluster that are belong to. So as you can see, if you look at the original image, it's just a matter of pixel value, right? So the area that is classified as the same as this area, it would be quite like chocolate or dark brown. So if you look at this one, this is kind of dark brown. This area also dark brown, and that the rest will be similar to white or blue, something like that. So they are grouping together. Okay. Mhm. So if we look at the label, so it's just 0 and 1. Then yeah, this is the mask. So you want to mask out some of the cluster. So this is we mask out this cluster and left only this cluster, the cluster number 1. And this one is just mask out the rest. So we just keep the second cluster and then mask out the first cluster. Okay, so that's how you did. Right, so that's the k-mean cluster. That's real quick. All right, so let's move to a unit. Oh, right. So the unit here. So let's look at the data that we are going to use. So here's the data. So I have prepared a subset of images for you. So this is the data set from Kaggle. So if you look at the image, so this is the image of a car. So we want to perform a segmentation on this car. We want to extract a mask of the car from this background, right? So we just want a car. So this is the image. So it just the image of the car from different angle. Okay, so this is the data set. So I have prepared the training image, and this is the mask. This is the mask. So this is manually, right? This is manually
Yeah.
prepared.
I want to create this one, this mask from the original image.
Yeah. So
So
you
use
have to
the Label Studio can do this?
yeah, Label Studio can do this.
Okay.
Yeah. So this is the ground truth, right? So this is our ground truth. So we want the model to predict this one. Okay. So next, what we are going to do is that first, let's just import something. Oh, too many sessions. Let me see. Yeah. Oops. Interrupt executions.
No, you view resources.
I'm sorry.
You have to cancel view manage section.
Yeah.
Manage down.
Select.
Okay.
And then I think this is already. Yeah, you have to pay. That's what happened when you are using for free, right? So let me see if it allow me. Okay. So here, so what we are doing here in the second cell is very similar to what we did in YOLO, right? So we define the dataset class. So we call a Kavana dataset, and then we have this image directory, mask directory, and then any transformations if we want to perform transformation like rotation, translation, something like that. And then this one is where it is the functions that we can use to extract the trainings sample from the data set, right? So it just reading the image from the photos, and then these are the masks, right? These are the masks in that we want to read it as a Gauss-Root. And then we convert the image to RGB, all right? And then for the mask, we also want to convert it into the grayscale image, all right? So here it's just nothing but we just specifying if the mask value is equal to 255, because if you look at the image, right? If you look at the image, it is black and white, but it's in RGB mode. So black will be 0, white will be 255. So when training, we just wanted to predict either 0 or 1. So that's what we are doing here. Just set it 255 to 1, right? That's it. And if you want to do any augmentations here, you can apply transformations. So when you apply transformation, you have to apply for both image and mask. That is the ground truth of the image. All right, so you just run that. And then this utility function is nothing but just to provide you for saving, loading the checkpoint. And then this function is just nothing but prepare the training data set, prepare the data loaders for validations. And so it is very similar to what we did in YOLO, right? So this is a data set. And then after you get the data set, you prepare the data loaders, specify the number of batch size, number of workers, and then you want to shuffle or not, right? So basically, when we train the models, we want to shuffle, but when we evaluate them, validate or testing them, we don't want to shuffle because we want a consistent result. So we basically not want to shuffle the data, right? So that's why the while loaders is setting shuffle to false, all right? And the rest is nothing. It's just for utility function like calculating the accuracy, right? And then this one is just to save the prediction image, right? So this kind of so if you look at this save predicted image, you can see that we use a model.eval. And then after that, after we finish testing, or after we finish providing the test image, we set the model back to train mode, right? So that's what we did. So now let's talk about, did I run this? Okay, I ran that. So now let's talk about the unit architectures, right? So I hope you remember this unit architecture. So this is the architectures of the unit, right? So this is a stack of convolutions, and then we perform downsampling. We perform downsampling, stack of convolutions, and this is the bottom next, and then perform upsampling, right? So how do we convert this into a code? So first we define this double convolutions, which equivalent to this. This is the double convolution, right? So we have 64, that is number of filters, and then this is the resolutions of the image, right? So what we are doing here is that this is the convolutions, this is the convolutions, and this is the Bash norm and Lilu, right? So this is one layers, this is one layers, right? So Lilu as the activation functions. So that's this is this part, okay? This is this part, double convolutions. So every layers it has double convolutions. So yeah. So that's what we did the double convolution here. What did I do wrong? Name it not defined. Let me see. I think I missed importing that. Okay, and then so we have double convolution, and then we are going to construct a unit. All right, so the unit, the in channel will be 3 channels, and then out channel will be 1. Right, out channel will be 1, and then we have the up and down. So up and down. This is down. This is up. Okay, and then this is the bottom next. Down, up, bottom next. So we define this as a module list. Module list means we can stack the layers together. So we now define this. We now already define this double convolution. So we are going to stack this together. All right. So what we are going to do is the down part. Okay, the down part. So this is the features. This is the feature, which means how many, the number of filters. Okay, this is the number of filters. So what we are going to do is that we are going to, so these features, it will loop to 64, 128, 256, 112, right? And then what we are going to do is that this is the double, right? This is the double convolutions. So what we are doing is that first we are doing this part, 64, 64. This is the first one, right? 64. It's taking this number and then construct the double convolutions and then add it to the module list, right? And then we are keeping doing this. After that, we are going to do, so the features here is setting up is equal to in features. So what do we mean by that? So in this layer, right, in these layers, we have in channel is equal to 3. So after we do a convolution here with 64 by 64, right? So output right here is going to have 64 filters. So we are going to feed this into another layers, right? Another layer. So that's why we have to set these features is as the in channels of the next layers, right? If you look at this, oops, if you look at this, so 64 here, we are going to feed this, the red dot here, the red arrow here. We are going to feed this as an input to the next layers, right? We are going to feed this into the next layer. So we keep doing this. We keep doing this for, so we're adding this to the module list. This is the list. So we just keep adding into the list. And then for the upper part as well, for the upper parts, we are doing the same thing, but reverse. All right, for the upper parts, we are using the COF transport 2D. All right, so that's the transport convolution we discussed earlier. right? So what we are doing is this part. We are doing transport back until here, right? So, and this is what we are doing, okay? What we are doing, something like that. So we construct this, we got this part, we got this part. So right now, what's left is this part, the bottleneck part here. So the bottleneck part is nothing but it's just a double convolutions, right? If you look at the structure, it's just a double convolution over here, just a double convolutions. Okay, so that's the double convolutions over here, and then the final layers, the final layer is nothing but just this part, this part. Okay, so it predict its output it output 388 by 388 and then two channels. Okay, because it's predict 0, it's either 0 or 1. All right, so but the thing left that we haven't done is this skip connection, right? We have to do a skip connection from the down to the up. We need to add a skip connection between the two, right? So now we are going to add a skip connection, right? For every down, for every module in the down, so we're the output from this down, we are going to keep it as a list of skip connections, right? So as we go down here, as we go here, we keep this into the list. As we go down here, we keep this into the list, and then we keep this into the list, keep this into the list. So when we go up, we're gonna take this in out from the list and then add it into this one, right? So what we did is that we go down, add it to the list, add it to the list, add it to the list, and then at the bottom next, you reverse the list, right? Because the list now you're gonna have a list of these features. It's going to add from layer 1, layer 2, layer 3, layer 4. So then when you go up, you are going to go from the very bottoms, right? So you're gonna take out the elements from the last one and then add it into these layers. And then when you go up to this layer, you can add it into this layer. All right. So that's how we add a skip connections over here. Right. So this is nothing but just test whether the model works or not. So yeah. All right. So here's the hyperparameters is pretty much the same, right? They're pretty much the same from here. I think I need to do this. I think I don't get this one. Right. So these are the hyperparameter. It's pretty much the same learning rate, training image, there, something like that. All right. So that's how we set the hyperparameters. And in this models, these are the transformation that we did. We have to do a resize rotations, horizontal flip, vertical flips, and then take a normalizations, and then convert into a tensors. All right. What happened here? Okay, so no data. Did I change the directory? Not yet. So I need to change the directory. I did or I didn't? I didn't. Okay, let me do it here. All right, so let's mount that. Right, so what is it? unit the unit, right? So yeah, and then something like that. Yeah, should works. Okay. So now what we are going to do is just to initialize the models, initialize the loss functions. So here we are going to use a binary cross entropy, and then we are going to use Adams as the optimizer. Okay. So let's see how many. This is how you calculate the training number of parameters and the number of trainable parameters. All right. So we can use this function to sum up to see whether this kind of architectures, how many variables or how many parameters our model have. Okay, so here we have how many 31 million parameters in these models, right? 31 million parameters, and the learnable parameters is also 31 million, right? So that's the number of parameters. All right, so let's see if it works here. Train function is not defined. I think I forgot to. There is no train. So can you write a train functions? This train functions. It should be very similar to what we did in YOLO, right? So I'll give you 10 minutes to write this train functions. You can have a look at this YOLO train functions. It should be pretty straightforward. Right? It should be very straightforward from here. So you can do this. Right? You can try to change this one. So let's take 10 minutes for you to do this. And then if you could, I think I encourage you to do the validation function as well. So you can take these orders as a validation image into the validation functions. Okay.
Bạn biết ạ? Trên function
Actually, gaming
So you get it? All right, so I think that the training function is pretty much the same, right? So we just have this like batch loading the data in, and then doing this targets, right? The target over here, and then perform some sorts of model predictions, calculate loss, and then perform some sort of this back propagations, and then update the weight. Okay, and I think this one is just pretty much the same. So here I set the number of epoch to 3 for simplicity, and then I just ran that, right? And then here's the result. So this is the validation ground truth. Okay, this is the ground truth, and then this is the predictions. This is the prediction. It's not good because why? Because we just training for 3 epochs. Okay, so that's why it didn't perform well, right? So it didn't perform well at all. So if you keep training, like for many epoch, this would probably be good. So for the very first epoch, like first 3 epochs, it just predicting everything, almost everything as 0. All right. So you can try like you can try with this many epoch, right? It probably perform much better. Right, so that's how we do the units for semantic segmentations. Okay. So any questions?
Just double check my understanding again. So you have the original image
Mm-hmm.
and you have the ground truth with the mask binary. So when you train with the training, so you compare with the weights and parameters and all. So you compare the training and load, and you compare with the ground truth that kind of specific pixel is matching with the training with the mask.
Yeah.
And then you if not, you update the way until we've finished all of the image and you get the best, I mean the most best of the training, right?
Yeah.
Right.
Yeah.
I just
So
compare the pixel by pixel
yeah,
for every image.
Yeah, you compare pixel by pixel for every image. For example, in this lab, what we want the model to predict is either 0 or 1, right? For each and every pixel, whether it's belong to the objects or it's belong to the ground, to the background. So this is our ground truth. So the models, it is going to predict this same thing, right? It's going to predict the same thing. For example, it probably predict this part as black. Let me see, this part as black, this part as black, this part as black, and then this part as black, for example. So this is not what we want, right? So what we are going to do is that we can calculate the accuracy of this image, and then we keep training this. We keep doing this for many epochs, so that the model learns what it has to do, and then it's trying to adjust the weight of that one. So yeah, basically we need to have a ground truth, so then we can perform we can let the model predict a mask, and then we compare the ground truth mask with the predicted mask, and we compute the accuracy from there, right? So the accuracy in this semantic segmentations would be the number of pixel that is correctly classified or correctly predicted. All right.
Yeah, clear.
Okay.
Thank you.
So, any other questions? All right. If not, maybe this is it for today. All right. So tomorrow we are going to learn about the generative models, that is autoencoder, vibrational autoencoder, GAN, which is generative adversarial network. So that's in the mornings. And in the afternoon, we are going to discuss about 3D visions and 3D deep learnings, right? So most of them, what we have been discussing is 2D. So now we are going to step up. I just want to introduce you to the 3D worlds, right? It's 3D deep learnings for there. So we are going to discuss about that, okay? All right. So I'll see you tomorrow then.
See you.
Bye-bye.
Have a
Bye.
good drinking.
You right. Drink
Try beer Hà Nội.
fresh beer.
Or Heineken. Oh, the Heineken in the north is so expensive. Don't try it over there.
In Ho Chi Minh is cheap.
Yeah, it's cheaper. There's a factory, Heineken factory in Hanoi, but due to the in Hanoi they just try to drink bia hơi and wine, so they don't prefer the brand beer like Heineken. Or that's why it's so expensive.
All right. Okay, enjoy. Have a good day. See you.
Bye.
Goodbye.
Ủa, Linh lên tiếng nhá. Hả? Anh rồi chỗ nào? Đây á. Cái kiểu giấy á. Nó có cái quán tên mình đây. Đấy.
Hello. Thế rồi.
Very near here.
Okay.
Yes. Sau buổi tí nào phải bắt gáp ở đấy. Năm rưỡi 6 giờ rồi. Tầm đấy là hơi